Hi, jury members, all those who are in this room with us today, and all of you joining us online. Welcome to Construction Worker Housing Division. Construction Worker Housing Division tackles a critical challenge impacting millions of Indian workers. Construction laborers often endure unsafe, unsanitary, and uncomfortable living conditions, with women workers facing some of the greatest hardship. The teams in this division have deeply explored these issues and proposed innovative solutions for dignified, high quality housing. I'm excited to welcome you all to the presentations of the Construction Worker Housing Division to see how these students aim to improve the lives of construction workers across India. My name is Dhanashri Mankar and I'll be the MC for today. It's my job to keep us on time, and I'll be taking this very seriously. Our finalist teams have put in a lot of hard work. They have submitted their project reports about a month ago. And today, these teams will present their work to the jury. So teams, you will have 20 minutes for your presentation, followed by a 10-minute Q&A. There will be a 5-minute break after that. You must all use those 5 minutes to take your component model out of this room and allow the next team to bring in their model. Now, the Construction Worker Housing Division has 3 jury members who have had expertise in net zero and resilient buildings. We have Monish Sripurapu, CEO and founder of Ant Studio. Hello, Monish. Next, we have Deepa Parekh, Principal at Sustainability at Kapadia Associates. Hello, Deepa. Our third jury member is Manjunath. He is an independent consultant, structural consultant at Manjunath & Co. Hello, Manjunath. These jury members have had 3 weeks to review the report submitted by the teams. They have looked at your work in detail and have already assessed your entry for the 10 contests of the decathlon. Teams, your presentations will help them hear your narrative. They will assess your presentation and your mastery over the solutions through a Q&A session that we'll be doing today. They may revise their scores based on what they hear from you today. So jury members, I'm so excited to have you all meet the teams today. I will need to interrupt people, including you, from time to time to help us keep on time. So please don't mind. I'm looking for all your support in this. Please keep your comments and questions short and to the point. Okay, so are you all ready to begin? Yeah. Okay. So our first presentation is from Team Samarthya. They have worked on a project called Saksham, the project for construction worker housing division at Bhubaneswar in Odisha. Okay, so team, welcome on stage. Okay. Team, you will have 20 minutes to present your work to the jury. At 15 minutes, I'll ring a signal like this. Okay. You won't have the 21st minute. That means at 20 minutes, I will ask you to stop and end your presentation. Okay. After that, we will have 10 minutes Q&A session with the jury. You keep your answers direct and to the point. Okay, team. Wish you all the best. The stage is yours. Your time starts now.
Imagine spending 10 to 12 hours building someone's house and then going to live in nightmarish conditions. And so we at Team Samarthya asked ourselves a simple but uncomfortable question. Can worker housing be stopped treating as temporary necessity and be designed as an essential infrastructure? The answer is Saksham. Saksham means capable or self-reliant, and that is exactly what our proposal is. We are Team Samarthya from a multidisciplinary team of 12 people blending architecture, interior design, and engineering, and we propose a net zero construction worker housing system for 200 workers in Bhubaneswar, Odisha. The problem that we identified is not invisible, but is often overlooked: overcrowding, poor sanitation, heat stress. So we started by defining three key principles: modularity, efficiency, scalability. Why these three? Because construction sites are dynamic. Modularity, where we worked on making the project reconfigurable universally because worker numbers change, site condition changes, and project phases change. Efficiency tackled aspects of sustainability, addressing static housing that fails in dynamic conditions. And scalability caters not just to our site, but every construction site condition. So we designed a system that adapts. Now, to design for our workers, we needed to understand the working conditions. Our project partner, Z Estates, is developing a large residential project of a site of area 6,679 meters square in Bhubaneswar for 200 workers, comprising of men, women, and families occupying the space during different phases of construction. Guided by Z Estates and our knowledge partner, Architect Studio, our design balances construction efficiency, user comfort, safety, and sustainability while placing women's safety at its core. The slide offers strong functional advantages through excellent connectivity and favorable southwestern winds, while also presenting key challenges such as heavy monsoons and a sloping terrain that may cause waterlogging. When looking at our rectilinear site, we decided to divide it into three zones based on activity and gender. The mass was then strategically carved to accommodate the predominant southwestern winds, creating courtyards within each zone. Each zone is self sustaining with independent courtyards and sanitation units. The central spine becomes the heart of the project and drives four key zoning strategies. First, centralization for radial access of shared services. Second, gender based zoning. Male and female residential clusters positioned on either end, with communal core acting as a privacy buffer. Third, accessibility, with multiple access points connecting for circulation. And finally, user centricity. Charbagh inspired micro courtyards that support recreation, comfort, and community. It utilizes the southwestern winds and ensures that the modules optimize the sunlight. The result is a master plan that is deeply human centered, which strategically organizes residential, communal, and service spaces to maximize efficiency, privacy, and accessibility. At the unit level, modular planning ensures repeatability, scalability, and construction efficiency. Each living unit accommodates 8 occupants in a compact G+1 configuration, maximizing capacity without compromising comfort. Openings on the north and south facades enables continuous cross ventilation. Bunk beds are attached to the columns which facilitate circulation. The first aid unit is designed for 2 occupants, enabling immediate medical response for minor injuries and emergencies. The dining unit accommodates 48 users, functions for both food and community space, encouraging interaction beyond work hours. A similar layout is adopted for female dorms. But how are these modules built? We have curated a kit of path system that includes columns, beams, and joineries customized to accommodate n number of people. Starting off with PCC blocks for foundation that are then connected to the plinth beam using footing and custom joineries. The primary plinth beam connects to the columns and to the floor formwork of secondary plinth beams. The columns then connect to the roof beams or extend to create a first floor. This makes up our project structurally sound and easy to build. Now, let's get to the details. In our design, the original single piece joinery that we had mentioned in our previous deliverables has been modified into a two-part connection system. This resolved the difficulty of assembling corner joints when multiple modules are connected. The split joinery allows screws to be fixed from both sides. To connect the floor and wall panels to the beams and columns, we use an L bracket. The, sorry, we use an L bracket, enabling easy replacement of damaged panels. The purpose of this structural modeling was to test whether our modular system is structurally stable and practical for real world implementation. The shear force diagram, the bending moment diagram, and deflection diagram for the complete structure shows that our obtained values are well within the permissible values. But we also want to improve the human experience. So we asked, is comfort the same for everyone?
Well, no. Comfort for a construction worker is not the same as other. It's the difference between surviving and thriving. Our design responds to this by first rethinking space at an individual level. Instead of changing space permanently, the foldable bed system allows the same space to shift between rest and activity. When opened, each user gets a defined personal space. When folded, while also relocating the beds, it frees up space, makes the room more usable during the day. This directly impacts user comfort mentally and physically. The ability to transform their spaces gives them a sense of ownership and flexibility, which is usually missing in worker housing. Similarly, the Juliet balcony is not treated as a conventional balcony, but a control threshold. While it restricts physical movement outward, it allows light, air, and visual connection, making the space feel less enclosed. From a passive design perspective, it supports ventilation, increases air exchange, dissipating heat, and improving indoor thermal comfort without relying on mechanical systems. Reliability in this context is not optional, it is essential. To ensure continuity, we address energy dependence through sand batteries. The sand batteries store solar energy as heat for up to 6 months, which can be converted back into usable energy when required. By storing 15% of the excess energy generated daily until it is charged, thus eliminating the need for diesel generators. While systems ensure connectivity, safety is addressed at the source. We use custom groove metal elements at entry points that generate a ultrasonic sound. That is the sound off system. These signals are picked up by the central receiver. The systems work passively and cannot be tampered with, ensuring constant security even during power outages. And most importantly, we're designed not just for the users but for the stakeholders as well. This digital twin is a smart app based system as acting as an digital twin of the housing, where project stakeholders can monitor space in real time. Through this app, they can oversee occupancy, detect unauthorized access, and manage material inventory. We don't just design this space, we give you control over how it performs. But performance is not just digital, it's embedded in the material itself. We use agricultural waste based panels made from paddy and wheat husky as a primary furniture material. These panels are waterproof, termite resistant, and flame resistant. By replacing conventional plywood, it reduces maintenance and lowers environmental impact at at a furniture scale. But can worker housing itself become carbon negative?
The construction industry alone is responsible for 37% of emissions, energy-related emissions globally, and 30% of the global carbon footprint. Our project is designed with this in mind. So we asked ourselves, where is this embodied carbon coming from? In a building, the structure is the largest source of its embodied carbon. We address this by using EAF steel, reducing structural emissions to approximately 6.8 kilo CO2 equivalent per square meter. We further reduce embodied carbon through the use of corrugated bitumen roofing manufactured from recycled paper and wood pulp, alongside similar low carbon materials such as cement fiber boards, rock wool, and gypsum boards from Saint Gobain. Together, they result in an embodied carbon of only 39 kg CO2 equivalent per square meter, a 78% reduction from our base case. However, reducing the carbon footprint of a construction is only a part of the challenge. Globally, buildings account for a third of the final energy consumption. To minimize operational energy use, we employ high efficiency BLDC fans and LED lights in place of conventional methods, reducing our annual energy demand from 722 kilowatt hours to 524 kilowatt hours per living unit. This results in a total energy demand of only 8,000 kilowatt hours for ventilation and 9,400 kilowatt hours for lighting per year. Solar water heaters, passive strategies such as optimized daylighting, natural ventilation, and an insulated bending envelope using materials such as uh, my friend is here to explain. Materials such as cement fiber boards, gypsum boards, and rock wool reduce energy requirements before any mechanical systems are even switched on. These measures collectively achieve an energy performance index of 17.27, representing a 38.5% improvement over our baseline. Yet, efficiency alone doesn't eliminate environmental impact. Even high efficiency buildings continue to consume energy. The annual energy demand for our project is 37,834 kilowatt hours. Therefore, we sought to not only reduce consumption, but to generate clean energy on site. Our solar panel system produces 58,000 kilowatt hours annually, exceeding our total demand and creating a surplus that we could sell back to the grid for about 88,000 rupees in income annually. So, what more could we do in terms of passive strategies?
Our site is oriented north-south with prevailing winds from southwest to northeast, while maximum sun exposure on the southern side is seen. The design responds through passive strategies to optimize ventilation and thermal comfort. North-south orientation reduces harsh low-angle solar exposure. Cluster planning captures breeze and reduces surface heat gain. Courtyards enable stack ventilation and improve air circulation. Opposing winds ensure cross ventilation and continuous airflow. Green buffers absorb rainwater and reduce monsoon runoff. This results in our operative temperature being 25 to 31 degrees Celsius year round. After multiple CFD analysis, we were able to optimize the size of the courtyard with respect to the prevalent southwestern winds. This resulted in the percentage of comfortable hours achieved annually to be 82%. The orientation and positioning of our windows ensure up to 65% of floor area receiving maximum sunlight while making sure the spaces remain glare free without hampering our total annual useful hours of up to 75%. Similar to the courtyards, our living units also maximize efficient use of wind patterns for internal circulation. But well being is not just dependent on thermal comfort. Sanitation is also an essential part of health and well being.
Starting with the core of sanitation, waste management in our design is treated as a continuous system rather than a one time disposal system. Waste is generated at source as seen in the plan and collected as per different strategies. Parallelly, grey water is treated through dewarts for flushing and irrigation. That described our post consumption strategies, but what about at the source? For most construction workers, water is not a guaranteed source. It is shared, unreliable, and often limited. So we begin by reducing demand at source via low fixtures which cut usage by 30 to 60% without affecting daily comfort. However, current systems rely on irregular supply and one-time use, making them inefficient and wasteful. To address this, we introduce a cyclic system around 12,200 liters per day of wastewater using DWATs and constructed wastelands with our partnership along with our industry partner Clear Aqua. This is further supported by rainwater harvesting, with appreciation to 2,02,500 liters collected annually from roof catchments. The water is filtered through a five-stage system with 90% efficiency, stored using a passive gravity-based system with multiple tanks ensuring availability even during dry periods. So instead of a linear system, we create a closed loop system where water is reused, reduced, and retained within the site. Together, these strategies ensure that a limited resource is not just conserved but distributed more efficiently. This directly enables us to reduce per person consumption from 140 LPD to 71 LPD, achieving nearly 50% reduction while improving access, reliability, and overall living conditions for every user.
Construction sites in Odisha are highly vulnerable to cycles and heavy rainfall, leading to wind upliftment and flooding. To address this, we strengthen structural connections, improve roof anchoring, and introduce slope management, rainwater landscaping, and elevated units, ensuring stability and safer living conditions. At the same time, the resource failure is a major challenge. With the irregular outage, we integrate on site treatment, 18,000 liters of storage, and systems that allow up to 3 days of water autonomy along with the energy backup. Finally, the design also addresses safety and well being. Clear evacuation routes and assembly points ensure emergency preparedness, while passive strategies reduce the heat stress, improving comfort and reducing dependence on mechanical cooling. Along with performance, the design also ensures that these strategies remain economically viable and scalable. We begin by comparing the baseline and proposed systems. Through material optimization and efficient planning, the cost per square meter reduces from 14,463 rupees to 9,438 rupees. This results in an overall 34.75% reduction in construction cost, making the system significantly more feasible at scale. But affordability is not just about initial cost, it extends into long term performance. Maintenance cost reduced by 76.56% due to durable materials and low dependency systems. At the same time, the design generates 58,514 kilowatt hours annually, resulting in 2.64 lakh rupees in savings, along with an additional of 1.1 lakh rupees through export revenue. When combined, this leads to approximately 12.2 million rupees in initial construction savings and around 3.65 lakh rupees per year in operational savings. So, the design is not just efficient and resilient, but financially practical, making it scalable and implementable in real life conditions. We began with a simple question here on: why should a developer invest in worker housing? Because this is not just housing. By bringing worker closer to the site, reducing daily travel time, improving well-being and minimizing absenteeism, it creates a more productive workforce that helps projects get delivered faster and at a lower cost. It reduces construction cost by 34.75% through modular steel framing, reduce excavation, and optimize material use. At the same time, it cuts long term expenses with a 76.56% reduction in maintenance costs using durable and replaceable components. Speed is another key advantage. With prefabrication and dry construction, the system enables 40 to 50% faster assembly while allowing parallel construction on site. What makes it more efficient is its scalability. It grows only when required from a single unit to a fully housing cluster, avoiding unnecessary upfront investment. The modular steel frame also allows unit to be assembled, disassembled, relocated, reused, making it a long-term reusable asset. Beyond construction, the system reduces dependency on external infrastructure. With solar energy, rainwater harvesting, and decentralized water wastewater treatment, it lowers operational costs and ensures more reliable performance. So, for a developer, this becomes a solution that is faster, lower in cost, scalable, and more dependable over time. But faster delivery begins with the people delivering the project. So we asked ourselves, after 10 to 12 hours of shift, what does the recovery look like for our end users? For us, it comes down to three things: a personal sanctuary to rest, safety without worry, and privacy you can trust. Because when workers feel rested, secure, and respected, they return to work healthier, more productive, and ready for the next day. Thermal performance plays a major role. The design increases comfort hours by 82% and keeps indoor temperatures up to 37.7 degrees cooler, helping reduce heat stress. Smaller interventions like the Juliet balcony bring in natural ventilation and daylight, improving air quality and reducing fatigue. So, even a small design move creates a high impact improvement in recovery and well being. Better living conditions, better workforce performance, faster project delivery, lower risk, higher returns. If one decision can deliver all this, it really is an expense. Or
Thank
is
you,
it the
Team
smartest investment
Samarthya.
on site? Thank you.
Thank you. You did a really good job. Now, let's hear jury's comments and take questions from them. Deepa, I'll start with you.
Team Saksham, good effort. Always a bit nervous, right? When you're the first one to go up on the stage, everyone else can relax a bit. Good effort. It was the presentation was clear. In your proposal, you have a very clear functional layout. There are actually many questions, but a couple of areas to start with. I think overall, some more resolution is needed to understand how best your design can work. Let's maybe go to, your actually here itself, your site plan is visible. Um, is it right that these courtyards are facing east,
Yes.
the open
Yes.
courts,
Yes.
right? So how is it porous to the southwest breeze?
Ma'am, because our winds are going to be going through the windows. I don't know if you can see here, but the windows are here. So the southwest winds come from there and they move through the site like this.
So yeah.
Just to add on, essentially our wind direction is south of southwest. So that is why the orientation is such. But predominantly it's seen as south to north in general. Yeah.
So even then, I thought wherever is your predominant wind direction, you want to ensure there is more porosity on that end. So something you should think about right now, your layout looks more opaque to that direction rather than being porous.
Ma'am, if you would allow me, I'll explain
Sure.
with the model. So actually, over there, the roofing system, it shows that the whole dining unit is one. But we have ensured that there's like four openings right next to each dining space. So the wind can actually pass through all of these openings along with the windows, maximizing the amount of wind and thermal comfort that we can achieve at this space. So it's not completely barricaded. We have ensured all of the directions are kept in mind for that. Like these spaces, opening spaces have been given for.
You should have tried an option in different orientations, like with the
Yes.
courts. We didn't see that sort of haven't tried a lot of iterations. So maybe this probably may not have been the best. Okay. And maybe just one, and then I'll pass it on to my other jury members. Something to think about is I think in your report you mentioned the total comfort hours is around 34%. Right now, you probably increased it when you were presenting. I'm not sure how because your proposal seems to be the same.
Ma'am, it's because when we had gotten the feedback, we realized that our numbers were wrong. So we did the simulation again and we realized that we had actually done some mistakes in the first in like simulation that we had done. So when we did the simulations again, we got that number. So that's why we wanted to present the correct number after that. So the
Okay.
34.4% is the one from the wrong simulations that we had done, and we checked it after we got it in the feedback.
Okay. All right. I will pass it on to my.
Thank you, Deepa. Thank you.
Yeah, okay. Guys, congratulations. I think it's been a fantastic effort. Very nice presentation too. The master plan is something I really like because of the courtyards and the way that you positioned it. And um, well, I think the density could have been a little bit more because practically speaking, construction workers, the developers giving this much of land with that density is a little rare. But the kind of spaces that you developed, I must say that that is pretty interesting. But the real life scenarios might be slightly different. You People might not actually get that kind of space for this. So that's the good part. I have only three questions very specifically on three segments. If time permits, maybe we'll ask more. Uh, one on the thermal comfort, affordability, and rainwater harvesting. So on the thermal comfort, again, the same point. I also spoke about this 34% thing in the comments, and you said 42. But what is actually more concerning is the 7% the degrees drop that you mentioned in the presentation also right now from the outdoors. I'll just let me complete. The thing is 7 degrees. Let's imagine in a real life how it like actually behaves, right? The space. Let's say the temperatures are more than 40, 42 degrees. If you have only 7-degree drop, it means that you're still at 35, 36, which is not actually comfortable for like beyond 32 is not actually comfortable. And having 34% of annual Earth's comfort in a space like this, because uh, if you don't do anything at all in this, like forget about all the passive measures and everything, the average comfort levels in a building are still like around 22 to 25, 27% is still comfortable without doing anything. So with all the interventions that are there, you only manage to push that threshold by probably after the simulations again 15%, and without the previous one, what you submitted is around 8 to 10 degrees, correct? 8 to 10%.
Yes, sir, I would like to correct that. The mentioned value was along with the previous simulation. So the corrected one is actually 14%.
14%, right? Is the increase
14%
that you're saying.
increase.
I'm saying that the overall performance could have been like could be much better because 14% from the baseline is slightly lesser. And I don't know, I think very briefly also mentioned about active measures. I think mechanical cooling also in the presentation or no? Okay. Okay, so you can only on the now
Those were
speaking
some
about
BLDC fans that we had
yeah
spoken about.
on the on the affordability thing, you have taken the baseline, the costing to be 1400, and of course, I mean, and then the after the optimization, it came down to 9,000 not costing. What is real is actually makes sense, but the baseline is like I think most of the teams and in general also is taken to be 1,000 rupees as the baseline. So why is your baseline on the higher side?
So the baseline that we have given is 14,463
Yeah.
and the proposed case is 9,438. So during that, we have taken into consideration that whenever we take our materials, as it is a pan-India design, how are we making the materials be usable? And these tin sheets are not as durable compared to the ones we have seen because this material sheets are used into each model and be it scalability, they also increase in the number of materials that have been used. In that
No, no,
case, we
sorry
would
to cut you. Actually, what you proposed is real. I mean, it's realistic. But your baseline for construction houses is on the higher side. What I'm saying is that the 1400 is normally much lesser. It should be the baseline has to be lesser. What you proposed seems okay.
okay.
Understood? So that's one thing. And then the last thing is that you like really good measures for the rainwater harvesting and everything, and you emphasized on it very nice. But have you considered the patches where because there are times when at least like 5 to 6 months when there is the when the housing cannot depend on rainwater harvesting. So what are the measures for when you're not depending on rainwater? What have you considered those factors?
So rainwater harvesting is sort of not exactly the only source of water for them. We do have the municipal water line that's coming over here. We're primarily using our rainwater harvesting to aid in case of any kind of natural disasters or if the municipal lines are irregular. So our rainwater will give us around 1 week of buffer. So in case the line is cut for say a week or if there's a disaster, we can cater to that. And if there's a shortage, we can always take it from there.
Thank you.
Thank you, Monish.
Yeah. So I think it's a very seamless presentation, but I think considering I just want to comment on structures because whatever you have conceived, how do you build this? So I don't have any slide which shows the way it is built. Huh? So one minute. Let me complete the whole thing. So how far is this site from the sea? Is it at the
Approximately 70 kilometers because
70
Bhubaneswar
kilometers?
itself is not a coastal city.
It's
The,
not a coastal city, but
no,
70 kilometers also has saline atmosphere.
70 to 80. Bhubaneswar city in general is 70 to 80. Our exact location is around 75 to 85
Okay,
around there.
okay. But it still is saline. Okay. So one is using, I think, tubular steel. You know how good it is for saline atmosphere. Is it galvanized? Okay. Then I just checked your plinth also is in steel. So how how guaranteed that we can have a steel plinth which is very close to soil and water. Okay. And then I really don't know what is the water table here. Okay. If there is capillary action, so that is one. Second thing is with consideration of such uh, you know critical natural forces in terms of cyclone uplift, has bracing taken into account for horizontal forces? Because bracing is not there. Even if you don't take bracing, probably is there a way that you can identify column locations through concentration and then fragmentation? And then the junction details, what you have provided for the beam, it doesn't indicate which is primary, which is secondary. Does the primary go through the slot and the secondary gets locked on to the cleats what you have provided? And the cleat what you have provided from the box section is holding the panel, rather it should sit over the panel, bracket. So these are, I think these are very critical in the sense that the idea is the building should age well, you know rather than transferring it through tension. Whatever is the filling, whatever the material, it may crush. Okay. and uh, and uh, and if you had given some sort of an isometric exploded view of the whole process, you will almost get how it can be built. Okay. uh, then the roofing is what is the roofing? Roofing is a sheet. It's a
Yes,
it,
sir. It's a corrugated bitumen roofing sheet.
it's a corrugated bitumen roof.
Yes, sir.
Okay, what is bitumen? Bitumen is the top layer, or it has an infill of particle board.
No, sir. It is a singular composite
Do you
material
have
that
a
is
brand?
ondulant, sir.
Ondulin. Ondulin is not bitumen. Ondulin is clay, red clay. It's red mud plasticizer, RMP. Just check on that. Okay, it comes from
Uh,
Australia, right?
Sir, actually, this comes from Penang in Malaysia.
Malaysia, Australia, yeah, maybe, yeah. So just check on this whether it is bitumen covered or it is red mud plasticizer.
Yes, sir.
Okay, that is one.
Sir, their company offers a lot of different things.
Okay,
What we
okay,
are
okay,
choosing
okay,
is
okay,
the corrugated bitumen
okay.
one.
So what are the walls? Walls are made up of what?
It is a sandwich panel which has gypsum boards on the outside,
Yeah.
sorry, a gypsum board on the inside, cement fiber boards on the outside, and rock wool in the middle for insulation.
What is the joints? How does this marry with the box sections?
As in, like, how are these held together?
Now, how are this married? How do you seal the joints?
Sir,
Is
using L
is it
brackets.
is it a tongue? Yeah, I don't see anything there. I see the box section. Okay, I see two knobs. I think the water can pass through, right?
Pass through
The
via
gap.
that?
The pass through the gap.
Yes, sir.
You wanted the water to pass through,
No, sir. I mean, you can pass through the sides, but not through it, of course.
but how do I think if I put a water bucket of water, does it go inside?
Like the gaps here. No, sir, we have sealant like between the joineries of the sandwich panel and the columns. We
Is
will,
there a better way of doing other than the sealant?
sir, that's what we have
Huh?
used. There probably is. That's what we have used, but there probably is a better way to do it.
Yeah. So if you do doors and windows,
Mm-hmm.
so do they use sealants?
That's what we are using, sir.
No,
Yes.
they don't use sealants, right? For the shutter to move, that is also a joint,
Yeah.
right? So I think what I'm saying is I think it's a fantastic project for you to make sure that everything is thought over. because the way it is built and removed, because it's a prefab system, right? So if there is something thought given to that, it's much better. After doing it, if the water enters, then what's the point, right? Yeah. Do you have gutters if you want to store water? I didn't see any gutters. No downtakes, nothing. You want to store water finally, that's what you were looking at, right?
Sorry?
You want to store the water, no?
Yes.
Where are the gutters?
So for the in the rainwater harvesting, we have it as the roof cutter. So that's above the roof area. It goes through the
I don't
gutter
see. I
pipes.
don't see. I don't see downtakes in your drawing.
Yeah.
There's no parapet, first of all. No, you need to hold the water to channelize to the gutters. So I think these are small details, okay, which we come all the way to see. Okay, huh? Okay, thank you.
Thank you so much.
Thank you, jury members. Thank you, Team Samartha. Let's take 5 minutes and get ready for the next presentation. Hi everyone. Our second presentation is from Team Zero. They have worked on construction worker housing project for ANP Privado at Pune. So team, you will have 20 minutes to present your work to the jury. At 15 minutes, I'll ring a signal like this. You won't have a 21st minute, which means at 20 minutes, I'll ask you to stop and end your presentation. After that, we will have 10 minutes of Q&A sessions. Please keep your answers direct and to the point. Okay, all the best team. The stage is yours.
India has a staggering India has a staggering 48.5 million construction workers, but the industry still faces a 47% labor shortage. This tells us two things. First, that construction workers are indispensable to India's future growth, and second, millions more will be needed in the years to come. If we expect more people to join this workforce, we can no longer treat construction work as a menial occupation. We must begin to recognize construction worker as the very people who build our nation and provide them with dignity, security, and quality of life that every individual deserves. And that begins with a place to call home. A very good morning to one and all present. This project is undertaken by Team Zero from SMEF Brick School of Architecture and VIIT Pune in collaboration with a project partner ANP Corporation and industry partner VKE, who questions the reality of those who live at ground zero. The project ANP Pravado is planned with an overall workforce of 1,500 construction workers, and the construction duration is almost 36 months. The construction worker housing is on a rented land which is 850 meters from the project site, which is located in Baner, Pune, and it accommodates almost 250 construction workers. The site lies in a warm and humid climate, and but according to the recent climatic changes, it is more on a warmer side at the moment. Throughout the project timeline, the workers are employed in a uh, the workers are employed by the contractors in a rotational and shared manner, and they're engaged in various construction activities. The users are migrant construction workers, majorly from the northern side, which is Bihar, Chhattisgarh, UP, West Bengal, and Uttarakhand, Jharkhand. There is a mix of both individuals and smaller families, and the working hour ranges from 7 a.m. to 7 p.m. The construction worker housing is planned on a 2,511 square meter site area, having a built up of 1,556 square meter, which includes the following spaces. The key role of the project partner was to develop a scalable construction working housing model which is replicable across various ANP projects and sites with the potential to be commercialized either through rental or by sales within the construction sector.
To even come up with the design of any construction worker housing, we analyzed how the current housing setups were actually done. Through case studies and site visits of the actual model that our project partner was using, we then tried out many design iterations on parameters like modularity, form, and climate response, through which the triangular form proved best across the parameters, giving multiple options for different kinds of practices. The triangular frame was designed to have a foldable assembly, giving ease of transport and assembly. 8 of these frames would then come together to form a living unit comprising 20 users across 2 floors, where the upper floor would be staggered 1 meter behind to make way for the first floor passage and staircase. This same framing could be repeated in a longitudinal manner, creating long units as per different site conditions and requirements. And then this could be topped off with a double roof, providing a thermal buffer as well as some potential for solar power generation. Together, these clusters provide mutual shading across the site as well as access to wind circulation. The triangular frame was quantified into an equilateral triangle of 3.3 meters with a depth of 6 meters, providing each user a floor square area of 5 square meters, with bunk beds placed on centrally and singular beds towards the sloping side. The unit plan was modulated to have multiple options for family and bachelor user types, giving shared as well as dormitory type possibilities. Again, the same framing could be utilized to form common blocks like kitchen, dining, creche, saving more costs on the framing and structural part.
To right size openings, we performed annual thermal comfort simulations on a variety of openings. We first explored the standard swing opening. In this opening, when in the open position, the opening itself could act as the chhajja. However, we noticed that when the opening was in closed position, it totally blocked ventilation and daylight. We then explored louvered options where the users had more control over daylight and ventilation. On performing annual thermal comfort simulations on these options, we saw that in the swing openings, there was a 40 to 60% of total annual hours of thermal comfort achieved. However, in the louvered options, there was a 60 to 80% of total annual hours of comfort achieved. In the lowered options, we then performed ASC and SDA simulations. In the ASC simulations, we see that in the standard lowered option, only 3% of the total floor area is exposed to harsh daylight. However, in the integrated option, around 16% of the total floor area is exposed to harsh daylight. Though there is a huge difference, both are within the acceptable range. However, in the SD analysis, there was a huge difference. In the standard opening, there was around 46% of floor area that received daylight autonomy. However, in the integrated option, more than 95% of the floor area received spatial daylight autonomy. This made the choice very clear, and we chose integrated opening as the perfect choice for our module. This was not just chosen based on the simulations, but also because of the design of the integrated opening, it allowed ventilation to enter into the module at two different levels, catering to two different kinds of users on the different levels of the bunk bed. We then moved on to the construction process. This construction process, along with the site development, is carried out in six major stages across. That takes around 21 days. The first stage is the foundation and the plinth setup. In the foundation and the plinth setup, we've used screw footings because it causes minimal disturbance on site and could be used in different kinds of terrains as well. For the plinth, we've used earth bag filling. The earth bags could be filled with material that is readily available on site, which could be the excavated soil or the construction debris. The second process is the second stage is where the structural setup takes place. We've used 50 mm thick 50 mm hollow EF steel sections that are bolted together to form the primary structural frame. In the third stage, the floor installation takes place. Along the bamboo joists that are fixed to the structural frame, fiber cement boards are laid and it forms the finished floor. The fourth is the unit envelope. In this stage, we've specially developed lightweight fabric walls. Now, these walls had been specially designed because they reduce transportation volume and also help in better handling by the users. This wall comprises of two 0.6 mm thick fiberglass fabrics. Between these two fabrics, there's 50 mm thick coconut coir insulation. Now, because the wall is fabric, we had to add certain elements to provide rigidity to the wall. So we introduced 50 mm thick manvale bamboo at 1.1 meter center to center distance, and this entire wall assembly is then stretched onto the primary structural frame. There were designated openings in the structural frame where the integrated window could be accommodated. The fifth stage is where the external element installation was completed. In this, there was an integrated bamboo railing clothesline that was installed. There are bamboo staircases that is installed, and the solar panels are installed. Then in the sixth stage, the services, mainly a hydroponic like system was installed. Now, hydroponic was selectively installed on surfaces where solar radiation was highest, that is the south and the southwest surfaces. This provided thermal buffer for the fabric walls. The fabric walls in itself also have low thermal conductivity, both the coconut coir and the fiberglass fabric, and have a very low value of 0.8. This entire construction process over different stages and all the components together create the entire unit module that accommodates around 20 people. On material integration, that is the fiberglass fabric panels, we achieve a thermal comfort of around 62 to 78%. Further, on the use of BLDC fans inside the module, the thermal comfort is around 70 to 84%. So the total annual thermal comfort hours is 6100 to 7300 hours. Now, because the module need not be site specific, since it is construction worker housing, we did the entire module into a kit of parts. The kit of parts were developed in such a way that it had three major categories. The first was the structural skeleton. This skeleton remained constant across all different sites. This The second was the adaptive envelope. The adaptive envelope changed with respect to the site and the context of the site. So different climatic regions had different adaptive envelope. The third was the service plugins. These were off the shelf components that could be readily bought and installed into the module. These these three categories together create a cohesive kit of parts that could be scalable and replicable on different sites.
So to come up with the site plan, we had a slightly different approach. We first designed the single module and then laid out certain guidelines on which site plans could be created for different site options, which would have guidelines like having clear segregation of bachelor and family units, having spaces like kitchens, dining centrally located or near an open space, toilets to be segregated as per the gender, and services to be located in the close proximity with a clear access, and also maintaining fires tender movement and other service vehicle movement. Through these guidelines, we have given various iterations of how the same module could be could work on multiple site conditions. These same guidelines have been applied in our site plan, where the drinking water facility is centrally located while the washing spaces were kept accessible near the entrance. The uh, toilets were gender segregated as per the zoning of bachelor and family units. So the overall intent was to create a simple assembly which had a compact inventory and hence came the 60-degree concept. But since what we know and what we've understood, we didn't want it to create any engineered infrastructure, but a designed housing for people who built our own.
Beyond the visible imbalance lies the measurable performance that defines its impact. After observing the design flaws and poor conditions of construction worker housing, we collaborated with VKE and established our core intent for innovation by redefining the baseline quality of living. This led to a three-step collaborative solution: identification, integration, its implementation using the inspection toolkit. Site supervisors conduct monthly audits to measure, verify, and keep check on every livability parameter. In the livability index, we established a set of quantitative and qualitative measurable parameters like thermal and environmental comfort, hygiene and sanitation, spatial dignity, social and mental well being, and safety protocols to redefine worker dignity. Secondly, the zero complaint app. To ensure these standards are scalable across multiple future sites, we integrated a centralized digital solution. The app streamlines livability through three modules: maintenance tracking, inventory access, and real time announcements, keeping operations smooth for both workers and management across any number of locations. Moving on to energy performance. We started with base case EPI of 38.66. We focused on three simple strategies. In the unit, each user was provided with their own 2-watt task light. We replaced standard 80-watt fans with high efficiency 18-watt BLDC fans. And thirdly, we optimized our outdoor and toilet spaces by using motion sensor LED lighting, eliminating energy consumption and operating time, resulting in achieving EPI of just 22.01. This represents 43% of reduction. The next step was to address how we generated that energy to achieve a net positive balance. If you look at our radiation analysis, we implemented a double roof system. The top layer consists of solar panels positioned to receive maximum direct radiation, which allows them to function at their full potential. We used 300 numbers of 165-watt polycrystalline panels. This solar DC power flows directly into central smart inverter. Our total energy consumption was just one-third of our total production, allowing us to send over 70,000 units of clean energy back to the grid each year. Our goal for water performance was to reduce dependency on external water tankers. By integrating strategies like low flow fixtures, foot operated taps, and eco sand toilets, daily per capita water consumption was reduced from a baseline of 135 liters to 72 liters, a massive 46% of reduction. Eco pan separates solid waste and urine at the source. The solid waste enters a dual pit system where it converts into manure after 6 months, while the urine is routed to the Camas STB for grey water treatment. With all these measures, we completely eliminated any black water generation, and our daily grey water generation was reduced to just 15,000 liters. Post treatment, this water is fully reused for cleaning and hydroponic facade, with the remaining water supplied to the construction site. Regarding rainwater management, we made a data driven decision because Pune receives an average of 700 to 800 rainfall, providing conventional storage infrastructure was not feasible. Instead, we shifted to a passive groundwater recharge strategy, utilizing permeable surfaces to naturally return over 9.5 lakh liters of water to the earth annually. For embodied carbon, by replacing conventional materials with fiberglass sheet, coconut coir, bamboo, fiber cement board, and EAF steel, we reduced the embodied carbon from 83.2 to just 35.2, achieving 57% of overall reduction. We conducted a risk assessment, dividing our strategies into two main categories: health and sanitation, and natural threats. Risk was mapped against major threat factors. Waste management failure, heat stress, and droughts were identified as major risks, which we tackled. For fire safety, our module uses a class A rated fiberglass fabric capable of resisting temperature up to 550 degrees Celsius. For power cut, our solar setup includes a 4 battery backup system that guarantees a full 48 hours of electrical autonomy. Also, while peak outdoor temperatures can heat up to 42 degrees, considering the heat stress in the today's time, a layered walling system and vegetative facade reduces direct sun exposure by 60%, and the site can function autonomously for 48 hours during water scarcity.
The main aim with respect to affordability was to spend more in terms of per person and reduce the cost per area. The cost per user in comparison to both the base case and the proposed case is approximately the same, which is 24,000 square meter. And the cost per square meter in the proposed case is almost 2.5 times less than the base case as you considered there, which was almost 9,000 square meter. The major reduction from the base case was majorly through our design form, framing, and construction methodologies that we adopted throughout. While the additions, while the addition to the base case were more in terms of the long-term investment, like solar power systems and efficient fixtures, and user-oriented additions like furniture and hydroponic facade. A 16 lakh solar investment, equivalent to 3 years of electricity expenses, recovers the cost in 7 years, generating a long term net saving thereafter. While the setup and operation cost along the life cycle of material and transport efficiency was also quantified. Built in 14 days, reusable across multiple sites, and capable of reducing the energy demand by 43%, water consumption by 46.6%, and life cycle cost by up to 50%, the proposal redefines the worker housing from a recurring expense into a high performance, revenue generating asset that delivers both operational efficiency and human dignity. Beyond providing shelter, the proposal fosters a safe, inclusive, and community driven living environment through gender sensitive planning and dedicated accommodations, vibrant shared spaces that encourage social interaction and well being. Supported by regular health checkups, women led welfare initiatives, and continuous site monitoring, the system prioritizes both physical and mental health. So, could the matrix be reduced or pushed a bit lower? Probably. But the question was not on how low the numbers could go, but how far its optimization could be taken ahead without compromising livability, security, and comfort, but rather deliver efficiency, resilience, and a quality of life for the people who call it home. Thank you.
Thank you, Team Zero. You gave a very insightful presentation. Now let's hear jury's comments and take questions from them. Manjunath, I'll start with you.
It was a lovely presentation. Yeah. But I think this. I think what is the usable area in the triangle? What is that inscribed square with the minimum height required for usable space? I think you are.
Hmm.
I think you put the cards up to the edge,
Hmm.
right? So when he's, I think you can sleep,
Hmm.
but
So we place the bunk beds in the central part and the single beds on the edges.
yeah, so
Hmm.
you sleep and then you can't rotate on the other side.
No, no, not
It's
the.
okay. It's
Huh,
okay.
not exactly to the edge of the wall. We'll keep a
Yeah, yeah, yeah.
certain distance.
So what I'm saying is, how does this isosceles triangle
Hmm.
or equilateral? You said equilateral or
Each triangle is an equilateral triangle.
equilize? So 60 degrees.
Hmm.
All
Hmm.
three. So what is that size? Is that the most effective structurally or usable? So if I were to look at this whole thing as a rectangular system with a brace,
Hmm.
you make a rectangular section and then I put a diagonal.
Hmm.
Then it becomes a right angle triangle.
Hmm.
So I can put right angles,
Hmm.
continuous. So it is a more orthogonal system only, right? So how does one decide about this angle, this triangle? It's like because if I look at more acute in the sense that I take, you know,
Hmm.
yeah, slightly
Understood.
deeper,
Hmm.
so I'm more comfortable. I'm just wondering, after using this place, do
Hmm.
the people walk straight or they walk inclined?
Hmm.
I'm
There were,
just, I'm just
huh,
feeling, I'm just
there were
feeling.
two
No, yeah,
reasons mainly.
yeah.
So first one was
Uh-huh.
the triangular framing was easier to install, and we were
No, this
able
is
to.
fantastic structural
Huh,
system. I love it.
huh.
I love it.
And
And then the intensity of you looking at detail, junctions. No, I'm not here to, look at this is good, this is bad. But I think it's a fantastic attempt
hmm.
to look at. I'm just looking at slightly away from the structure in
Huh.
the sense that,
So when we do a 90-degree structure,
yeah,
what usually happens in CWH is the contractors they tend to place more people in the same living unit, which is like way too much dense, and
right,
the livability gets somehow compromised. With this form, there is a limited
yeah.
density control that you can do, and hence we were able to give each user a 5 square meter, like a reasonable range of floor area.
So do you elementalize production and assemble as elements to make this whole, group of elements?
Yes,
Yeah,
yes,
it's
yes.
fantastic. Thanks, thanks.
Thank you, Manjunath. Monish, over to you.
Guys, great presentation to start with. Uh, what I really enjoyed actually going through your presentation is the attention to the detail and where you actually made gave the thought to every single the component that goes into it
Hmm,
and how you're actually making this rightly what you said the kit of parts where things can be put together
hmm,
and the whole idea of starting with the collapsible system the triangle in the first place and transportation is also mentioned. I think that's also one of the reasons why I actually specifically
hmm,
asked you guys about even the transport emissions because that would strengthen your case to pitch
hmm,
because you're talking about transportation as one of the parameters in your case which in a typical case might not be that relevant
hmm.
because here you were saying that okay we're going to manufacture it and we're going to send it. So
Yes.
that's one thing. But one thing that I could not really stop thinking about is while the structural system is like really stable, it's beautiful, it's innovative. I think kudos to the team because you really thought beyond the mainstream to think how you can make something really innovative for the construction housing. But the only slight drawback, which I could
Hmm,
also mention in the comments, is on the side
hmm.
like when you look at the two membranes on the side where you have actually spoken about the planting and also the windows,
Hydroponics, yes.
the hydroponics, that's what is actually prone to the water ingress. The detail when you have junction and also the skylight that is coming in
Hmm,
is the one that is actually extremely prone to waterproofing. So have you guys considered because you have two faces?
hmm,
One is the inclined one and also the front and back.
hmm,
The front and back could have been that permeable and the windows and the like one panel could have been a door and the other panel which is opaque could have been actually a modular window system.
hmm,
And whereas the sides actually could have been non-permeable,
hmm,
could have been for planting so that
huh,
eliminates any chance of any water ingress.
hmm,
And I mean, what I really liked is that this is scalable both vertically and horizontally.
hmm,
While you actually currently have shown only two,
Hmm.
That's because of you having this permeable membrane on the side and the windows. Had you removed that, it could have been like scalable, like placing these containers,
Hmm.
these triangular ones units, both vertical and horizontal. Except for the, I think, like I said, overall, it's a great attempt, and happy to see the presentation.
Thank you.
Thank you, Monish. Deepa.
Okay, well done, team. Great effort put into your entire project. I'd like to first mention that you had a very unique team role, you know, designated to your members, which was like calculations team, graphics team,
Hmm.
simulation team. It was not as per the contest like how we usually tend to have.
Hmm.
I found that to be very smart, innovative, and a different way of looking at it. And then it was like an expertise, and then you can, work on it on any of the
Hmm.
contests, right?
Hmm.
So very good with how you thought about dividing your team roles. I also like that you thought about livability index.
Hmm.
I mean, this is one of the things that everyone's trying to solve, better working condition and all of that. So, and I heard you talk about all the parameters, but is there some index that you came up with, like some number, some qualitative, I don't know, grade or something? I didn't see that anywhere.
So we created this matrix in which we like did various parameters which were qualitative as well as quantitative, and we identified what a method of testing for each one of them could be, and then what kind of a result is preferred to assume it as livable or consider it as livable. Like there were
Yeah, so it
different.
has a list of things and not like you've come up with one
Hmm.
sort of a grade or anything, right? That the index is like a one or a two or something like that. It isn't anything like that, right?
Hmm.
Okay, all right. Something to think about. Maybe you can come up with your own.
Hmm.
So it can be assessed, right? Different
Hmm.
projects can be assessed based on this sort of a
They were
index.
qualitative and quantitative. So some of the parameters we could quantify, like the
I know
temperatures or
everything
the
rolled into
AQI.
one also gives you
Hmm.
a way of looking at a
Hmm.
project entirely.
Hmm.
Yeah. Okay. Is there a reason why you picked a 165-watt panel? Because you get higher wattages,
Hmm.
solar
Uh,
panel. This
we
seems to be very low.
we calculated how much the electricity bill would come in the 36-month period, and then we back calculated it how much investment could be made, and like try to equate that. So
Okay. You could go with what is available,
hmm.
which is of a much higher wattage,
Hmm.
and then say that, okay, you can even generate surplus. Or maybe
Ah.
you don't need as many panels.
Hmm.
You can just do away with less. Yeah. Okay. Some of the other things, although you went by very quickly, which is talking about thermal comfort.
Hmm.
And you mentioned here on that 24 to 30 degrees is what you can achieve inside your units. But you also mentioned heat stress in your report,
Hmm.
where, first of all, in Pune, temperatures can go beyond 30 also,
Yes.
right? And your simulations also show that your indoor temperatures are about 2 to 3 degrees higher than outdoor temperatures.
What higher?
That's what your so anyways, let me say the main thing is if you want to test how it would function when the temperature could go up to 42, that's what you've
Hmm.
mentioned, you should also then run a simulation for that.
Like a selective time period.
Yeah, in a free running building, which is like naturally ventilated building,
Hmm.
there is not too much of a delta between outdoor and indoor if you keep all the windows open for ventilation. Okay. You may not achieve a 10-degree drop
Hmm.
because it's not
Hmm.
cooled
Not temperature.
mechanically.
Yes.
And so to say that it can go up to 42, but ours is in the range of up to 30
Hmm.
is not the right
Ah.
comparison. Yeah. So just work upon that. And yes, there are several areas that can be still resolved further, but overall, great job and sincere efforts into your project.
Thank you, ma'am.
I just want to add, in continuation to the same idea, if you can look at this whole triangular as elemental,
Hmm.
uh, if you can look at the same cuboid, imagine if you look at the cuboid and you connect the diagonals of the cuboid,
Hmm.
okay? you get a form which is seamless rigid.
Mm.
Okay, then you can assemble, then make the structure even more effective.
Mm.
You got it? What I'm saying is,
Yes, yes,
if
yes.
you connect the surfaces, diagonals of it, you get this beautiful connection. That is the seed, which is triangular, which is an outcome of a cube.
Yes, yes.
Okay, if you assemble it, you make the building.
Mm.
It's much faster. Okay, that's the clue. That is the seed of mind which I'm giving it to you.
Yes, yes.
Huh?
And one last thing is that while as a module it's great, your site level organization needs some more thought. It doesn't look spacious. All of that you're trying to provide spaciousness and all of that inside the module
Mm.
is there's a lot of effort into thinking through it, and then but on the site it was just looked like it was just placed
Because the
based
brief
on the
we
available need.
received from the project partner had a lot of workers on a very smaller site, so we tried to accommodate as
Yeah.
closely as possible.
All right.
Thank you, jury members. Thank you, Team Zero. Okay, we will be taking a small 15.
The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through
Hello all. Welcome to the presentations of Construction Worker Housing Division. Our third presentation is from Team Greenprint. They have worked on a project called Tunnel, which is located in Trivandrum in Kerala. Team, stage is yours. So team, you will have 20 minutes to present your work to the jury members. At 15 minutes, I'll ring a signal like this, which means you won't have a 21st minute. At 20 minutes, I'll ask you to end your presentation. Okay, after that, we will have 10 minutes Q&A sessions. Please keep your answers direct and to the point. Okay, team ready? Your time. Okay, let's get ready. Okay, your time starts now.
Yes. Good morning, respected jury members and everyone present here. So, our team Greenprint is here to present a problem faced by the construction workers of our country and address a solution to it. So, when we first began this project, we thought of the lives of these construction workers to be rather poetic because they built our homes, and yet most of them live in these temporary tin sheds that are hot, unsafe, and discarded after every project. So, tunnel is our response to that problem. So, tunnel in Malayalam means shade. So, we propose this net zero, resilient, and reusable structure that becomes an infrastructural asset to the company while at the same time improving the well being of the people living inside it. To reiterate the problem, so basically, all across India, in all the construction sites, these workers are subjected to very adverse living conditions. They are people too, and they deserve better living conditions. And in India, the problem is treated as a temporary necessity rather than a designed living environment. So we teamed up with a group of like minded individuals who wanted to provide dignified housing for their workers as well. So our project serves a site that houses 137 occupants, including 24 children. That fact is important because the site has a high tension line running through the southern part of it. So we need to protect the occupants from the radiation interference. And another challenge that we faced is the contours that run from the northwest to the southeast direction. The wind direction was also primarily from the northwest to the southeast. So we have used these challenges as opportunities instead in our design decisions to make it uh, optimized, to make an optimized solution. So, right from the beginning, right from excavation, we have thought about circularity in our site. So, we used a closed loop earthwork strategy, and we are only excavating less than 60-meter cube of soil from the site, which we will use for infill on the site itself. This will cut down costs for transport as well as disposal problem. And then we use helical screw pile system in our foundations so that we can reduce the cut and fill even further. Coming to our design, basically we have zoned it according to the contours to provide comfort and privacy for the three groups of people who are living within our site. So we have bachelors, we have family units, and we have female accommodation as well. So we have used the natural contours of the site to provide privacy and naturally provide circulation to these three different groups to maintain their privacy and comfort. We have located the family and the female units to the north of the site towards the higher point to provide privacy, and we have located the bachelors towards the southern part of the site, providing larger gathering spaces for recreation for the site overall. The common spaces, including healthcare facility, the creche facility for the children, as well as the kitchen and the dining spaces, are provided such that it is easily accessible throughout the site. The toilet blocks are provided in each site, as is the kitchen as well as dining spaces. So our site and project does not simply look into the function. While it responds to the functions very exactly, it also looks at the people who are living within them, the lifestyle of the people who are living within them. So the construction worker lifestyle is such that they start their work early in the morning. So our tunnel prepares, lives, and protects them throughout their daily life as well. So we have provided spaces for different age groups of people, the children, the crash facilities, the uh, the middle-aged people who are using the recreational facilities as well. So it responds to the daily life of the worker living within it.
The assembly sequence starts with the driving of the helical screw piles with a tractor mounted drive heads, and then later on the columns are erected on the head heads of the pile plate. The primary beams are connected to the columns with stud extensions from the column with stud extensions from the column sleeve. The second following by the secondary beams and floor and roof grids. The wall system consists of a solid panel, service panel, a door unit, and a window unit. The which are standardized dimensions to ease the production, ease of assembly and disassembly. We have bamboo mat board for shading, and for roof panels to secure that we have provided slide lock purlin cleats to prevent from the wind uplift. Uh, our our system can be installed in 45 days, which can be dismantleable, reusable, and repairable. This is possible with the unique selection of the materials used for the panels. For roofing, we have used insulated metal sandwich panel with a 75 mm PIR. All these materials are adapted based on the U value, the carbon emissions, cost, with comparative analysis of different building materials with the conventional systems. Flooring material consists of fly ash cement, HDPE, and bamboo composite. The wall material has layers, and then window material is of polycarbonate with a timber frame, and the light gauge primary steel framing is used for the primary structure, which is easily uh, lightweight, transportable, and can be dismantleable easily. The foundation and substructure used are helical screw piles, which are adaptable to the terrain, and these leave no trace at the site when which can be dismantleable and reused at another locations.
Let us now analyze the wall panel which our team has prepared. So basically we have a core cellulose panel board, and exterior we have recycled Tetra Pak based panel board, and interior we have we can either use bagasse particle board or rice husk particle board, which is basically having similar properties. So in Kerala, Trivandrum, the rice husk particle board is available in abundance. So we are looking forward to that. The sample which is presented is bagasse particle board.
Health and well-being, when we look at the health and well-being aspect of it, so we looked at integrating passive strategies from three aspects, that is physical, mental, and social well-being. So physical well-being mainly looked at the building orientation, cross ventilation, stack ventilation aspects, because the comfort on the indoors are mainly affected by air and also the sun, that the sun radiation that falls into it. So optimizing the physical well-being through these strategies also improves the health of the construction workers, hence having a positive impact on their mental well-being, which helps with the reduced labor turnover as well as high productivity. And considering the laborers come from different places, they are still coexisting as a community on a construction site. So we have introduced gathering spaces, biophilic design, and also provide them with a sense of safety and privacy through our design strategies. So when we look at the indoor spatial quality, one is definitely the daylight. So although we did start with daylight autonomy, we looked at a threshold of 1000 lux for 250 hours on annual basis as our threshold, and looked at what are the overlit hours inside the space throughout the day. And that was done with three scenarios for different fenestration sizes, based and how it was placed based on the heat, which site receives the highest radiation. The highest radiation that received were in the order of east, west, and south. So the windows were mainly placed on the northern side, and lesser fenestrations were placed on the remaining southern and the eastern sides. When we look at the wind simulation, we looked at the low mean age analysis, which talks about the amount of fresh air that needs to be brought into the spaces. That is also the ACH as we look at. So we looked at the constant wind speed, that is zero point 0.4 meter per second at the ground floor and the upper floor, and looked at how which spaces and how often, like what is the cycle time that the supply air is coming in, which was 10 minutes at the max the cycle time, and also how these fenestrations are catering to the cross ventilation in the second one. So with all these analysis that we did and also the material optimization, so we looked at the adaptive thermal comfort simulations that were done for as a comparison from the base case with just the wall optimization, where the adaptive comfort hours were around 50%, and we looked at what if we optimized all the materials for the units itself, which went on to 54 to 58%. It was lower for the ground floors because of the shading coming from the upper floors, and for the upper floors, it was slightly lower, and ground floor was more comfortable. And when we also included the fan assisted cooling, where the wind speed was taken as zero point 0.8 meter per second instead of zero point 0.4, the adaptive comfort increased to around 78% for the upper floors and also 84% for the ground floor units. So we looked at a stepwise analysis for the adaptive comfort.
Let us now look at the energy or the EPI, which we can say. So basically, the Solar Decathlon India had provided us the baseline EPI of 35 kilowatt hour per meter square per year. So there are two scenarios, which is in green and which is in red. So the green one is the one which we designed using energy efficient electrical appliances, and the red one is if we are not using the efficient electrical appliances, or if we are using some like standard grade, which takes the EPI slightly above the SDI benchmark, which is given there. So by this, we are improving 22% of the total EPI. So moving on to the next slide, here we have the breakdown of solar generation of electricity through solar means. So here we have used roof mounted PV array. So we can get the net energy surplus of 1774 kilowatt per hour, which if we quantify into monetary benefits, which is 4 lakh 26,000 rupees per year.
Summarize on the optimization side of the design. So we have improved on the daylight from 23% to 97% in terms of comfortable by reducing the overlit hours, and also the internal operative temperature is from 28.7 to 28 degrees, where it's just zero point 0.7 degrees. But considering Kerala is a warm and humid climate zone, so humidity does play a role in it, where that is why heat stress has becomes a major parameter parametric to consider the indoor comfort, where the wet bulb temperature, where if it's higher than 30 degrees Celsius, it becomes uncomfortable. So that is also reduced with the materials that we're introducing in the cross ventilation from 95 hours to 32 hours. And the ACH is improved by orienting it through the wind directions, the existing wind directions, natural wind direction. And with these optimization, the adaptive comfort goes from 50% to 78%. And also that is reflected in the reduced requirement for fan assisted cooling also. And hence our energy usage reduces like accordingly.
So let us now understand the water circularity which we have considered. So uh, here are the four bars which we have mentioned. There, the total freshwater demand is nearly 33 lakh 16,000. So that liters per year. So here, if we adopt total rainwater which we can harvest and on-site grey water treatment which can be also reused. So we can actually get a net positive surplus that is 1.13 million liters per year. So we are not just wearing the badge of zero heroes, we are actually implementing it on the site. And regarding the water strategies, the treatments such as DVATs and wetlands. So this we are making sure that the water which we are being recycling, it also is being recharged in the aquifers, and as well as we are reducing the demand from 135 liters per capita per day to 66.28 liters per capita per day, which is actually a very good number. Let us now move on to the embodied carbon analysis, where because of our like reusability of the materials, we have reduced up to 86.7 life cycle, 86.7 percentage. That is from 1,136. So this 1,136 is if we go forward with a traditional construction of the construction worker housing. This is for a single use. This is 1,136, but 604 is that when we are using it for 4 times. So here, if we consider a single use, that is 151.2, we can get the reduction of 86.7% of total carbon emission, which is being reduced.
We look at resilience, construction sites are also prone to hazards and emergency situations as well. So we look at how evacuation also can be integrated into the design itself. And when we look at the evacuation time to be under 3 minutes, it's not an assumption we are making, but a calculated value we have arrived at based on the average horizontal walking speed of human beings and also the vertical descent. And we have considered the farthest unit from these staircases for their evacuation and this calculation time. So on an average, it comes down to around 3 minutes. And also with regards to other resilience strategies, the heat stress has already addressed, looks at the wet bulb temperature when it's higher than 30 degrees to be reduced. And considering Kerala receives intense rainfall, there's a chance of flooding. And that has been addressed during the site planning itself through retaining wall and bioswales in our landscaping design. And the fire safety, while there is an evacuation plan we have, also the materials do have a certain fire rating to it. And with the introduction of renewables, it reduces its dependency on the grid for energy usage, making it more efficient. So, since there is also a problem of how construction worker housing is not given much prominence because it needs to be uh, built very fast to avoid any delay with the actual project construction, we integrate the timeline of the 45 days that it needs to be set up into the actual project timeline to reduce any redundancy. And with respect to the affordability, every time the builder has to invest a new amount of money for the construction worker housing, we are proposing a multi-deployment solution where it's a one-time investment which can be reused for at least minimum 4 times, which is achieved through the material mix, where we are replacing conventional materials with bio-based and recycled. So instead of just creating new investment, we are redistributing the existing investment into these materials such that the durability of these solutions are increased and they don't have to invest repeatedly. So, with respect to value proposition, there are multiple stakeholders that are involved, not just the laborers, not just the builders. So, the contractor who works closely with the laborers will see that there's a reduced labor turnover and also healthcare savings. Companies and investors can gain ESG benefits through these strategies. And market scalability also has an impact, as this solution gives them a more long term aspect to it. And the solar investing in the solar energy also has a payback of 4 years with the numbers as mentioned earlier.
The collaborative innovation continues and intense, and feedback loop was used. The collaboration of multidisciplinary team members like from architecture, environmental, structural, and infrastructure design management, along with the faculty mentors and industry experts. Uh, we have arrived at a very cost-effective, worker-centric system. The continuous collaboration led to the innovations of cellulose filled SAP panels, recycled Tetra Pak boards, helical pile foundations, DVATs and wetlands, and also for foldable furnitures, and effective solid waste management with a
Thank you, Team Green Print. Hear Julie comment and take questions from them. Monish and Sandy.
Hey guys, very good presentation. Very detailed in terms of like how you went about the technical analysis, the response to the site. One thing you did not very specifically mention here, which is also the high tension cable, the line that is moving around, and how you actually configured your entire master plan according to the terrain, the cut and fill. So in terms of the design, like I said, holistically very well balanced, no doubt about it. One thing I found pretty interesting is your argument about the capital amortization, where you are actually not arguing that the systems that you have built in are actually cheaper, but you have invested, but then that gets recovered over four life cycles. I think that is a very strong and a valid point, um, but it's also very sophisticated to start with, because every time that you deploy, like what happens to the storage, like I mean, in a real life scenario, how it translates is a slightly complex and sophisticated. But yes, I think the idea that you guys actually went in to think about how the materials um, and the project behaves beyond one life cycle. I think that's something really interesting to see. And one thing I also found very like, I think where you spoke about the thermal comfort, I think there is a 8 degrees drop in temperature. Uh, that is something that again we need to look at it detail, because 8 degrees drop in peak summers is actually not.
So it's supposed to be point. It's point 0.8 in the end
Yeah, yeah,
slide.
but in the other slide it is called 8
It's
degrees.
8.
Yeah, yeah.
It's
Not, I'm
point
not
0.8.
referring to this. I'm talking about the 8 degrees.
The last.
Yeah, but I think being Kerala and also the high humidity values, you emphasized on the need for cross ventilation and the windows and all. I think that's also like really nice. So I think overall I've thought it is uh, what do you say, a very good effort and detail in terms of how you went about the whole thing. So the cost and the embodied carbon, the reduction, they're connected, right? I think the 86.7% embodied thing you're talking about. While, like I said, it's a good start to do this, I think, but I think it probably deserves much longer and deeper conversation to validate what you guys are talking about. Yeah, very good attempt.
Thank you.
Thank you, Monish. Deepa, over to you.
Okay, so first of all, a great start to your presentation. The pace was good, it was clear, and I liked how you opened your presentation. Also, kudos to your effort to speak without reading. It is not that easy to do. So I applaud your efforts to speak, through your whole presentation. Uh, my question to you is, before that one comment, I would have loved to see some more renderings. There's no visualization of how your project looks other than like one section and a plan. So it would have been nicer to have more of those, some 3D views, etc.
Okay.
You want to? Yeah. Yeah, that is it. So it doesn't give us a full picture of how you visualize your design proposal. Yeah. So it, if that needs to be worked upon. And I also like that you talked about wet bulb, very important in a hot, humid kind of weather. And that understanding of wet bulb is, that you brought in to for the comfort is something I really like. However, your whole this wind simulation, this needs some more exploration. If you do one time CFD, in fact, there isn't much wind speeds inside the units as we can see in the report.
Um,
And you are making the basis of ventilation as the thing to achieve all of this comfort, adaptive comfort percentages, which is much better because of and of course ventilation is an important part. So you see that wind pattern across proposed design. Inside the units you don't see much of a airflow.
Uh,
Okay.
Actually, the image here is quite small. It's our mistake. The actual one, there are flow lines, light blue lines that are there that flows through wherever the windows are placed. And
No, I could see that in your report. Those velocities seem very low.
Okay.
And secondly, you also have written prevailing winds entering at 4 to 5 meter per second. What's incoming?
Supposed to, yeah,
There, you've written there. Are channeled through the central courtyards.
like
So,
that
yeah,
is the outdoor
yeah.
winds, but the indoor that we've considered for the simulations is point 0.4 on a average basis that is usually seen in indoor spaces for indoor operative temperature simulations.
So, 0.4 also is very low to perceive like a lot of breeze or, you want elevated air speeds to perceive comfort. So a good way would have been like if, yeah, this is on the outdoor and maybe in the courtyard, it's open courts. It's nicer because it's more than 3 meter per second. But inside, when you're saying, oh, all of these arrows that you show, there has to be enough evidence supporting that this is actually how it's going to travel. Yeah. So while you did some simulations, maybe it gave you a sense of, oh, there's going to be an airflow. And so let me make that diagram. But that is not substantiated, especially when you've done so much of your process based on how well the comfort is achieved and so on. So some more deep dive is required. And also looking at multiple scenarios and not only one. So like a different direction here, for example, seasonally what happens, right? So just look at it all around. Then I think it would have been more convincing. And another question to you on daylight is you've mentioned you've taken a basis of 300 lux. Is that like relevant for a residential space?
No, the threshold we have considered for the daylight is 1000 lux for 250 hours throughout on an annual basis. That's for ASC that we've considered.
So basic daylight autonomy, we have taken the 300 lux, and this is considered because the occupant hours for our site is basically after the hours of working, and they are not involved in task lighting or any other sort of situation. So for this situation, we thought it apt to use that 300 lux threshold, which is also on the basis of lead version 4.1.
So you made a great point. First of all, if it's after hours, this data is not going to contribute much, right? And then it's all about artificial lighting. Secondly, for residential, it's very high because you don't do writing and other kind of tasks. So the thresholds can be lower, which means it can be more daylit. And you could maybe, look at windows a bit differently and to optimize for airflow rather than, daylight. Maybe make it bigger so you have better airflow, but then control it with ASC.
Yes.
Yeah. So these metrics may not be relevant for the type of work being done in the space. So to review that is important. So your baselines are, more reasonable and appropriate for the function.
Okay.
Yeah, that is about it. Thank you so much.
Thank you.
Yeah.
Thank you, Deepa.
Can I add one small point related to
Yeah.
what? Okay, guys. Yeah. So regarding the Bhubaneswar and also you guys, like especially when you're talking about thermal comfort, because both are hot and humid, airflow plays an extremely important role. That's the reason why we're emphasizing on the CFD part. And also, I think all the teams should actually talk about the drop in temperature seasonally, not just the 8 degrees, because that doesn't really communicate the actual the scenario. It varies according seasons.
Thank you.
Can you just show the structural? So can you show me the build also, the whole building? Is there a drawing for that? The architectural drawing? No, I think this is the plan. So how do I know that this is ground plus one? Is there, you have second floor also?
Sir, for now, it is not there for this side, but we have
So you
approvals.
have master plan for ground floor. Then where is the first floor? You have first floor? No. So where is the cross section? See, I think the whole complication is I don't see cross section. Is that it's complicated to draw? What is the topography in the sense that is there a survey plan? Is there a topographical plan? But this is what is critical for structure. See, you say I'm going to screw it onto the ground. Okay, imagine if you are screwing at a higher level, okay, what will happen to the low level? So, how do you build plinth? How do you align the screw into the ground vertically? So I think techniques should never be done in isolation. Technique is a requirement for the particular site and for the particular load. So without knowing soil SPC, soil bearing capacity, how do you adopt this structure? What is the SPC of this site?
200,
Huh?
200 to 250, sir.
250 ton per square
200
meter.
to
Huh?
250, sir.
So what? It's a Moram site. Then what is the topography in terms of what is the level difference from the higher to the low level?
Sir, it's 3 meter dropping over
For what length?
9, 19,
90 meters?
9, 36.
So, but it's not clear, na? It's not yet clear, right? So that is one. Second thing, when I look at this whole, you know, expanded view of your structure, how do you build it? So you say the head of the screw is going to be the base plate for your column.
Yes.
Huh?
Yes, sir.
Can you just go to that? So how does I read this whole thing?
Sir.
Is the building is on stilts?
Yes, sir. It is steel,
I,
galvanized steel.
I don't see from this from your expanded view. It's not very clear at all.
Sir, galvanized helical screw pile with.
No, it's fine. That pile is then the head. How does the head connects to the column?
Sir, it has a base plate over the head.
Where do I see? I'm just watching. There's no base plate. Okay. Then there is a tie beam. Then there is HDB waterproofing. Is it on the ground? This whole thing is on the ground?
Sir, the helical screw pile will be under the ground, but
Right.
till from the head of the helical screw pile till
Head
the
is
levels.
exposed. Head is exposed.
Head is yes, sir, somewhat exposed. Like,
Okay.
and then from there we can adjust the level of the plinth from, like, if there is contour on one side, it can be like from the plinth to the head level. We have adopted adjustable.
Okay. So you have to drive all the screws at the same level. How do you
Yes,
manage that?
sir. Actually,
So I think these are complications, yeah. So what we need to look at is this connection between each element is not very clear. right?
So head of the screw pile will be a square base plate, and to which the column has
But it's
extension
not
has a
it's not very clear. Okay, then what is the wall system?
wall system we have previous.
No, but in the drawing, on the drawing,
So, sir, there are door units, window units, and
yeah.
solid panels.
So it's all prefabricated.
Yes, sir. These are all
So what is the inner panel made up of?
cellulose for the wall system.
Cement with polystyrene balls,
No,
polystyrene.
sir. Actually, for the
Sir, this was done for the sake of component model due to
Okay.
the unavailability of
Okay.
cellulose panels
Okay,
of
okay,
that thickness.
okay.
Yes, sir. So basically, in our actual design,
What is your wall thickness total?
sir, 108 mm.
108 mm, including finish.
Sir?
Including finish.
Yes, sir. Yes, sir.
The wood finish in the inside, on the inside, and then cement on the outside.
Yes, sir. Sir, the Tetra Pak panel board will be visible outside.
This one.
Yes,
This
sir.
one. Okay.
And the laminated bagasse particle board is on the inside.
How are these connected to these boards? Is it mechanical or is it adhesive?
Sir, it is adhesive, but we make sure that it is not a VOC. The glue which we have also used is not
Okay,
a VOC.
fine. Whenever there's a cut, how do you seal the joints? When you cut the cross section at the doors and windows, how are the thresholds handled?
sir, these panels has a we have
I think why I'm asking is it's not clear in your drawing.
this
It's a cross section is fine. How do you can't allow this to be exposed because all the water goes through that.
Yes, sir. Sir, this was for the sake of
Okay,
component
okay.
model. We have tongue and groove arrangements which can be used so that the water doesn't leak inside the system.
Then the second point is you're not shown the structural analysis at all. Where's the analysis for this building? Ground plus 2.
Sir, it
And
is
how do you make sure that the load is transferred through screws?
sir.
It's not there.
In the report, we have attached in the annexure part.
No, but where is here? In your presentation? But how do I see it in the sense of I have questions.
Sir, it was
Because depending upon the load, what is the size of this screw and what is the depth of the screw?
Sir, these helical screw piles come with a diameter of helixes of 8 inches to 16 inches, and with a variable depths from 3 feet to 10 feet. These depend on the load which
What
under
is your
which the
load? What is your load coming?
Sir,
What is your
is-
maximum load on
it's
the
320
structure? Huh?
320 kilonewtons, sir, for
Okay.
one column at the intersection of two modules.
Maximum, I'm talking about maximum.
Yes, sir, maximum 320 kilonewton.
32 tons.
Yes, sir.
Huh?
320 kilonewton.
Huh? Yeah. Just check on that. Okay. What I'm saying is, it should be very clear, no?
Yes.
I think that finally you need to build this, right? If it is approved by your vendor, you're going to build it.
Yes.
Right? That is that. The whole purpose is that now. Right? The whole purpose is that if you win it, okay, then the vendor is going to ask you to build it.
Sir, actually, we have got vendors for the helical screw piles manufacturing, and they have these helical screws already available. And when
I think
even
what I think this whole thing is about clarity. I want the clarity. How each support is, how each floors are connected. Because this is as a unit, it's fine, no? As a unit, it's fine. How the next floor is going to come?
sir,
How the columns are going through?
Sir, the columns are of like 3 meter.
No, I understand all those things. Is it something which can be discussed like this, or is something which I can see? Because all the things can't be discussed, no? Or so I think that clarity is missing, in your presentation.
Sir, actually, they mentioned column sleeves, sir. Column sleeves over the column.
But I don't see it. Okay. Do you have a model also somewhere outside this whole thing? No, sir. No, no.
Architectural diagrams detail, but it is in our
There's no detail which is shown outside. No. Okay. Anyway, thank you. All the best.
Thank you. Thank you.
Thank you, Team Greenprint. Thank you, jury members. Let's take 5 minutes to get ready for the next presentation. Hi everyone. Our fourth presentation is from Team Sugriya. They have worked on a project called Triumph. It's located in Jaipur in Rajasthan. So team, you will have 20 minutes to present your work to the jury. At 15 minutes, I'll ring a signal like this. At 21st minute, I'll ask you, 20th minute, I'll ask you to stop and end your presentation. After that, we will have a 10 minutes for Q&A session. Please keep your answers direct and to the point. Okay, team, all the best. And your time starts now.
Thank you. Okay. So, good afternoon, everyone. Before we begin, I would like you all to have a look at these seemingly random collection of items I have in front of me. And I would also, they all have one thing in common, and I would like you to think about it. We'll come back to this later. So, our project's name is Triumph. And when we started working on this project, we we had the question, why design for construction workers? Because whatever is there currently is seemingly enough for the construction workers and everyone involved. So we'd gone on live case studies throughout Jaipur to understand the typologies of housing. So there are three main types. For small scale projects, you've got like people living on the ground floor or the basement in basically partitioned rooms. In medium scale projects, you've got people living in the setback. And in large scale projects like our project partners, uh, they have separated land available for housing only. But if you look at the screen, you can see that all the materials here are of very low quality, and there's a lot of third class brick, fourth class brick, and tin sheds. And there are almost no standards to hygiene or safety or even planning. So we had kind of wanted to, like, in our approach, like, target these problems and propose a solution that would be easily replaceable into the current kind of mindset of the people living there. So next please. Team Sugriya is made up of 14 undergraduate students, and we had partnered with Mahima because it's one of the largest real estate firms in Jaipur, and they have a sustainability first approach, which really aligned with our vision. So,
Our site lies in Dholai, which is located in the outskirts of Jaipur, western Jaipur, Rajasthan. The city center is accessible within 30 minutes, maintaining proper connectivity with major roadways and transportation hub. We conducted preliminary analysis of climate and found out that our site is experiencing prevailing winter winds from northwest and summer wind from the southwest, with an average wind speed of 7 kilometers per hour, which may be exceed to 10 kilometers and 12 kilometers per hour. Our site has three-phase connectivity. There is a groundwater borewell in the northeast corner of the site. We have a site area of 2090 square meter. As per the Jaipur bylaws, we have a ground coverage of 45% FAR2. Coming to the program requirement, as per the estimated estimate given by the contractor, we have 300 workers and 50 children on our site. As we can see by the worker demographic, out of total, we have 66% bachelors, 16% couples, and 16% children. Further, the workers will be using the accommodation after the working hours, approximately from 6:30 p.m. to 8 a.m. They will have their lunch break of 1 hour in between their work hours. The project partner reach out us with the following needs, such as family housing and crèche and medical room. After conducting thorough research and face-to-face interaction with the workers, we come up with the following solutions, such as affordable housing, safety and assurance, and health and well-being, and proper sanitation. After summarizing all the data and demographic given by the project partner, we came up with the suitable area program for the site. We have divided the housing into bachelors and family. Our site is relatively smaller in comparison to the number of workers to be accommodated. To overcome this constraint, firstly we excluded the whole site, then we cut out the courtyard to create a buffer zone between the unit. Our site has only one entrance, that is in the northeast, which is connected to the main road. Main road. Courtyard also create a stack effect, thermal regulation, and cross ventilation throughout the site. We have divided our planning into three zones. First is bachelor units. In the coming to the design, in the bachelor unit, we have bachelor unit. We have 48 units in total, 16 on each floor, measuring 22 square meter in area for people accommodation. In bachelor unit, we have provided washrooms in each floors, and there is a breakout spaces which serve as a service area also, and also as a sitting space. For the family, in, we have 47 units in total, 15 on ground floor and 16 on first and second floor. There is a separate washroom for male and female workers. There is a laundry area, and for the secondary spaces, we have different spaces like mess, first aid room, crèche, and like supervisor room and electrical room. Dining area is on the north side of the site, which is closest to the borewell and receive morning sun. Our mess works in two shifts of 150 workers. Crèche and playground area is connected to the family unit for the safety and assurance of the children. First and second floor plan, we have used typical floor planning for the first and second floor plan and separated some units on the to create a balconies. On the terrace floor plan, we have placed solar panels facing south sun. These are our bachelor and family unit layout that we will discuss later. For the landscaping, for the landscaping for the landscaping, we have different kind of plants. Like for the air purification, we have used snake plants and aloe vera for near the living quarters. And for the shading, we have used weeping fig and bougainvillea and curtain creepers. We have used lemongrass as a mosquito repellent for near the windows and washrooms. And we have used recycled tires for the planters and the seating. Passing to over the
So until now, you all have seen like that our walls have a very undulating structure to them. I would like you all to think about what that might be, and here's a hint. So the materials that I'd mentioned earlier, they all have paper core tubes, and like we've also used paper tubes as our main material. So I know what you all must be thinking. Wait, what? Paper tubes? So let me explain. Uh, Paper tubes are actually a very versatile material, and they can be recycled up to 20 times without losing their initial strength. They are very cheap and readily available. They have a low embodied carbon, and they provide good acoustic and thermal insulation. Also, this material has been used in previous like disaster emergency projects and has been used very successfully. But also with paper, you have your problems such as vulnerability to fire, water, pests. And we assume that paper would be a very weak material given our interactions with it. But I would like to say that when in the form of a tube, the geometry makes it much stronger and much more resistant to normal weathering forces. So our basic component is a tube of 75 millimeters diameter and 3 millimeters thickness, which is the basic we need for structural stability. And one tube would be around 3 meters, which would weigh around 1 kilogram. So in the base case, we have gotten a U value of 1.88. And in some situations where we want a larger thermal mass, we can include waste cloth fill inside. And this can actually be sourced from a lot of places in Jaipur as it has a huge textiles industry. And with some other interventions, our final U value comes out to 0.55. for waterproofing and fireproofing, we've decided to keep a layer of polyurethane, which can be removed and recycled later. And for fireproofing, a layer of water-based intumescent paint has been applied, which chars upon burning and prevents like the fire from spreading to the rest of the material. So now that we've seen the basic model, like the basic component, let's see how it fits together.
So now you all know about what a paper tube. So now we'll make a panel out of it. So to join a paper tube with frame structure, it is too difficult to join because it is two different materials. So we introduce a plus sign aluminum plug to join a paper tube with frame structure, and we kept all the panels standardized so we can work easily at the site. And we also kept two variation at the panels. One is for door and one is for window opening. This is the bachelor unit plan. Uh, a total weight is around 1200 kgs, and there are 47 of the modules. Uh, as you can see, the sectional elevation of the door side wall and the window side wall. We also kept hinges on the panels to reduce the volume of transportation. Uh, Same way, this is the family unit, and also we planned design strategies for this. First is easy assembly, second is easy transportation, standardized panels, and reduce labor and cost for this panel. Okay, this is the stages of construction of module. First stage is to install the foundation, which is alternate foundation, uh, pen foundation, and RCC foundation. Second stage is to attach structure with foundation, which is mainly primary structure. Second stage is to add flooring, and the last and fourth stage is to add panels with structure. The modular components are be prefabricated offsite and are be expected to transport on site by using trucks and tempos. This is the simulation that we did, solar radiation simulation, to know all the surface which will have more solar radiation and less solar radiation. Uh, this is the daylight simulation that we did to calculate the lux inside a room. We kept a small lux inside the room because it is a construction where the availability of the user is on the night. So at the day we kept less lux to prevent heat load at the night. This is the mesh comparison before giving clear story window and after giving clear story window. As you can see, this is the passive design strategy. For different modules, we simulate different simulation and achieved different comfortable hours. So maximum comfortable hours is 70% and minimum comfortable hours is 53%. And there are the different iterations that we tried out. This is the graph mapping comfortable hours, and that is the simulation that we did for before using of paper tube. We used brick wall as a another material, and another one is after using paper tube. So this is the structural system. We simulate this structure system on a BIM software, and beside this, we also calculate manually. We used ISWB 150 and ISMB 150 as our primary column and beam structure, and these are the further calculation. Also, we use two type of foundation, which is first is pen foundation to increase the percentage of transport of the modules across the side or in different side, and second is RCC foundation to counter the lateral load or other loads. And this is the calculation of carbon, embodied carbon, and the final embodied carbon is around 2,95,000. And the most effective materials for carbon, embodied carbon, are cardboard tubes and the recycled aluminum frames that we use on the panel.
Now talk now talking about energy consumptions. As we know, the total energy consumed in our site is around 59,513, and the and around 89% goes for their dwelling units, and around 16 goes for the common spaces, and around 1.4 goes for the utility spaces and the orientations. And this is all what we calculated, and we find out that we have a proposed EPI around 20.6, which is good for energy efficient building. And for energy generation, we have a solar PV panels over our roof, and which generate around 3 lakhs 3 lakhs kilowatt per hour, and as I mentioned earlier, we consume over 59,513. So surplus energy goes for the grid at the rate of 3.65 rupees per unit, and which will generate around 9 lakhs annually. The benefit of solar PV panels are clean energy and earn income, low maintenance, and energy security. And then we talking about the water performance. We have a groundwater and a rainwater harvesting in our site. So through rainwater, we will use as washing and a bathing purposes. This is all what we conclude for the water performance. Then we have a resilience. Around we have plenty of time to on case of emergency to vacate the site. Now talking about affordability, this is our baseline, and this that one is our proposed costing. This is around, came up to be around 51 million, and it's 2 million. It's just because we have a long term plan for affordability. Then we have a civil cost of around. Uh, so in which we have around in the civil works we have a 4,000. Can you explain this, the baseline and the proposed? The baseline is generally due to the thin materials and brick materials, third class brick materials. 2 million is 20 lakhs. Yes, sir. And 51 million is 5 years. Yes, sir. The thing is, we talk with the industry partner for industry partner for the long term plan for the 25 years, just because we we uh, we saved around 30% in around 25 years. This is our life cycle cost. And talking about the affordability for the panels, we have a 12 panels, 12 paper tubes per panel, and we're 75 per tube. So it came up, and we are utilizing 1,583 panels in our site. And the cost of per panel is taking around 1,500, including the fire coating and a water coating over it. This is our life cycle cost. 1,500 per watt. What is the unit? 1,500 rupees per square meter per panel. Size of the 3 by 1, 3 meter by 1 meter. It's 1:2. You should always give a per square feet or something, not per
But square foot is much better, no? How much is it per square foot? 3 meter by 1 meter, 3 square meter.
Yes, sir.
What is the cost? 1,500 rupees, 50 rupees.
1,500.
500 rupees per square foot.
Yes, sir. 500 per square foot.
I don't know.
Square meter.
Square meter. 500 rupees per square meter.
So you're saying 50 rupees per square feet is the cost of the panel? Yeah. And talking about the transportation purpose, we generally use the local vendors to minimize the transportation cost as well. And the value proportion is generally based upon the solar PV panels, over on a life cycle cost of 25 years, and like we saved around 30% cost, 30% saving from a initial costing, baseline costing. Uh,
Sorry?
What is the length of this tube?
3 meters.
You get 3 meter tube?
Yeah.
Yes, sir.
So we hope that through our design that we have addressed all the issues that we had stated out earlier, and that this material is something that can be easily deployed and implemented. So I would like to end this presentation by kind of acknowledging all the help that we've received, and it would not have been possible without them. Thank you to Mahima Group for giving us this opportunity and our industry partners for their help in this domain. Uh, we also took a lot of reference from Shigeru Ban and his works and his research papers to understand the values of whatever we're saying. And thank you to our faculty members for their guidance and support. And yeah.
Thank you, Team Sugriya. Okay, now let's hear from jury and take their questions. Deepa, I'll start with you.
Okay, thank you, team, for the presentation. Even I'd say that your report is also good in graphics and it's clear to read. Um, Good exploration with something new that we've seen in this category so far. You also have about 300 workers that you've accommodated in your site. Um I want to, I'm curious to know, you mentioned that your project partner is a sustainability first approach they have. Uh, what what is their feedback on your proposal,
Usually, like I'll tell you
especially
what.
with the cost?
I can start by saying like what they do regularly. So they usually give low class bricks and tin sheds, which they kind of repurpose into the site and the parapet infill and everything. And but the thing is that on a site like this, having that kind of material means you've got basically slums in that area. So that is one thing. The other thing is that we're giving a solution that Mahima can use again and again. So there are a few problems with the costing in the sense that it's maybe too much when we're trying to replace a baseline, material. But I would say that if more research is gone into this and the development is gone into this, so it can actually kind of the cost can be reduced. And also we've tried to implement the solar panel strategy as a way to kind of make it more beneficial for our project partner.
So on that front, your difference between baseline EPI and your proposed is not very different, meaning
Hmm.
the delta is not very great.
Hmm.
So if you are saying that's the only way you're going to recover the cost of this, then it may not be very viable because the savings is as per the electricity, as per what you showed. So that's one thing to think about. Second thing is you're talking about reusing,
Yeah.
whereas this doesn't come across as a super durable material compared to like a brick, for example.
Okay.
And I think you've mentioned you're replacing it every 6 years
Yeah, matlab,
in the report.
Actually, it's a thing like the project timeline is the 6 years. Then its replacement it's done just before if traveling happen and if they undergoes for any damage and all, then it's goes for a replace. If they don't have it, then it's perfectly fine to reuse in the next site.
So can you say that this material has a life of 20 years?
Yes, ma'am.
Okay.
In one of Shigeru projects, he made a church and like schools out of this material, and they lived for around 20 years without much damage to the structure, and that was because of all the interventions to the tube. And we've also had similar interventions in our design, but our thing will be facing more rigorous use. So even small things like someone putting out a cigarette or maybe fire accidentally coming in contact with it, those issues will be mitigated. Then if in any case there were issues in the panel, you could easily remove it and replace it, and otherwise it will not be much of an issue.
Taking into consideration about the costing, it's 51 million and the thing when we included the furniture costing and the every like finishing costing as well. Also, the baseline costing just included the civil works and uh, remaining costing as well. Just so it's uh, seeing huge, but on a scale of 25 years, we saved around 30% compared to the baseline. So, like, again. Okay, so in each project they need to make a new one, taking into consider 2 million for the six projects, let's say. So they need to use like next slide.
Okay, you're saying that they have to build a new one, whereas here you can repurpose the same thing.
Yes, yes, now. So we are saving around 30% from comparatively to baseline.
I'm quite sure the other two jury members also have more questions on this. So I want to ask you a different question. Uh, if this panel, like in your design scheme, if you simply make your design the way it is with bricks, would it be different? Or is this the only thing that is making your project better?
I mean, with bricks, for one, the I guess value is much higher than what we've achieved through paper tubes. And also, bricks are a very heavy material as compared to these tubes. And in one way, you're kind of saving on structural costs because we can use lesser um,
So let me
dimensions.
reframe it a little differently. You've mentioned you went to the site, you saw the plight of the workers, the way they live, and clearly it was not a great thing. With your design proposal,
Mm.
are those conditions better for them?
Yeah, because we
And
have
the reason being only this material choice or the way you've designed your units and everything coming together on the site. So
it's
that's why I'm
actually
asking, if you
both.
swap the material,
Mm.
would it still give them a better quality of living or not?
I would say no, mainly because of the thermal insulation factor, and also because bricks require a lot of like time to kind of build up. And if we were to make a three-story structure with this, it would be a very tedious process, and a lot of project partners don't want to give that much time into making construction worker housing. So this is kind of something that can be shipped and packed and then like reopened in like less than 2 days or something.
Okay, thank you.
Thank you, Deepa. Monish, your turn now.
Yes, a very good effort. The presentation in the 3Ds, and also like visually speaking, the building looks pretty very good. And like definitely the effort that went into developing these details and the prototype is also like really good to see. But uh, naturally, whenever you try something new, that also brings a lot of questions.
Yeah.
So that's the thing that we have to bear that cross, right? So one thing that really comes even before we get into the material is the number of joints. So whenever you put a panel like this, and especially like the paper to paper, the junction that is coming, it's a thin line. So even if there is a slight expansion and contraction, it is bound to water ingress all across. And the number of even the cross that you have shown in the base and all the junctions that are there, they all actually become the weak spots and the many of them when it comes to especially the rain. And so that naturally brings to the question, which I also asked in the comments is, why didn't you think of overhangs? Because there are two things for the, like the overhang, not right now, that is pretty, very less, but much more larger. So that protects the whole building from the rain ingress itself, like purely from the perspective of design, still getting what you're trying to do, would have been a design strategy in itself
Okay.
to cut off the water that is coming in. Okay. And speaking about the costing, I think you guys are way off both at the baseline and also at the realistic costing too. Because 50 rupees for this panel, something like this, if this is possible, every project would be doing this with paper, with a layer of bitumen, with borax, and also the fire proof material that is there, right? And the whole process itself of actually making this makes it like really expensive. And you also spoke a lot about the recyclability of it. But the moment you put these layers on top, does the paper tube still retain that recyclability?
Since we've put the polyurethane on the like the innermost layer, we can kind of remove it and
No, it's not possible. So once you add all of these layers on this thing, think of, forget about this is pretty complex. Even what people use, like the thin coating on the coffee and tea cups that were there, renders it unusable because there is a layer of plastic that comes on top. So having much more complex layers does not render it recyclable at all. Number one, it's very difficult to segregate these materials that is there. So one of the key challenges, I think, while the effort and what you tried doing in here is like really, I mean, we can see the overall the design and everything, but the material in terms of an Indian context, when you're talking about something like this, especially with a lot of joints and the panels that are there, each panel having again, like probably 15, 20 odd joints that are, all of these things makes it, I mean, these are the things you actually think about when you're talking about a product development, when especially that is your major design intervention, is something that you really need to look into. So one last question about the costing, which we were talking about, is the baseline 20 lakhs for the overall project could be something where developers or the project partners typically just bring metal sheets and just erect these areas that are there, and not a baseline which is comparable to something which you have otherwise done with the regular materials. So the baseline comparison could be for you two stages. One is what the project partner is actually doing on their site, that is what the budget that they have catered to. And the other thing is that, okay, for a project like this, if you do it with standard regular materials, this is going to be something that is there. So the variation that you're showing between 20 lakhs to 5 CR, then it would come down because what they would otherwise do. And the material costing, like I said, your panel, that 1500 rupees per square feet or like 50 rupees per square feet, or the panel cost seems quite off, because the moment you put a lot of layers, I think the costing will be much higher. So your the 5 million or the 5 CR costing would go much, the CR costing that you're talking about goes even much higher. Okay.
About this, we actually like kind of the like Sky India is our paper tube partner, and they said that they can kind of add those layers in their process of manufacturing. So that kind of removes of cost, because the like borax and all these other materials are not that expensive. That will like 50 rupees was just for the tube, and we gave an estimate for the panel overall. So uh, there's a little bit of a discrepancy between both of them.
Okay. Thanks.
Thank you, Monesh.
Yeah. Can you just all these are taken as non-structural or structural?
These are non-structural.
So I think this is a structural, it's a structural material. I think these, why are these tubes used otherwise? For what purpose?
Uh,
Huh? Can you hear me? Or it's too? So why are these, what is the purpose of this tube otherwise?
we chose these tubes.
No, no,
We were going to.
what is the purpose of this tube?
It's just
Not here, not here, not here, otherwise. Because this is done for something else, right?
yeah. It was used as kind of like single story individual dwellings.
No, no, no. What I'm saying is these tubes usually is used to roll cloth, right?
Cloth and other materials. They can be
Paper,
used for
whatever it
shipping.
is. Yeah, yeah, right, right. So the basic use of these tubes are basically to roll cloth and then stuff. This is basically a structural element. Imagine if this were to be used non-structural to structural, okay, then the cost will reduce. Cost will reduce. Yeah. So now if you look at this as a panel which is buildable as a unit, as a wall panel where you can transfer load, and to keep this stable, if you pre-stress it, in the sense that if you take the cable through and confine it, because these tubes are basically good in compression, very good in compression. So you can confine this through cables which are going through, then you can make this structure very stable.
Okay.
Okay, because it requires a strong base, where that base can be used to confine this whole non-compressible tubes. Okay, then you can make the structure very stable. And but in your case, the floors are not. Now you have a steel skeleton with an RCC slab right now, right? Or what is the floor made up of?
It's
The floor is made up of concrete board.
Concrete boards. So
Yeah,
you have steel frames and then you have concrete boards,
yeah.
right? Yeah. So if there is one material which can be used both vertically and horizontally by through tension cables, it would, make cost comparable. I think the cost is very high now. Looks like, you know, because I don't know how do you seal these vertical joints, which is once again a problem. Then how do you see the joint between the pipe and the frame? And how does this whole frame get into the structural frame? So all these things are open-ended things. So as an idea, as an idea is fantastic. It's a fantastic idea, so that it's very light and structurally very stable. Have you tried this to be used as a floor?
Paper tubes?
Yeah.
No, not as a floor. Not. It will take point load, but it cannot take point load. Sorry, but as of now, we didn't try as a floor.
Okay.
Because we have to provide a plane surface, so we didn't find out to
No,
get a
you,
plane surface on a paper tube.
if you can sandwich this paper tube,
Yeah.
okay, between two surfaces, like a honeycomb. They call it
Yeah.
as honeycomb. If you can do a honeycomb floor,
Honeycomb.
yeah, so it is also possible. Anyway, it's interesting. Thank you.
Thank you, sir.
Thank you, jury members. Thank you, Team Sugriya. We will now take a long break for lunch. We will start the presentation for Team Knit at 2:30 p.m.
The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world's so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and the world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through
Hello, everyone. Welcome to the Construction Working Housing Division presentation. We will now continue with the rest of the presentation. Our fifth team is Team Knit. They have worked on a project called Weave, located in Bangalore and Karnataka. The team stage is now yours. Um, welcome. All right, so rules. You will have 20 minutes to present your work to the jury. At 15 minutes, I'll ring a signal like this. Okay. And at 20 minutes, I'll ask you to stop and end your presentation. Post that, we will have 10 minutes for Q&A sessions. Okay. Please keep your answers direct and to the point. Are you ready? All right, team. Now your time starts now. All the best.
Good afternoon, everyone. We are Team Knit, presenting Project Weave. While designing, our team sought out to answer 5 questions. What is the problem? What did we learn? What did we design? And why does our design work? And most importantly, why should you care? So, what is the problem?
Every city, every road, every highways, every overpass is built by hand, by people who travel hundreds of kilometers from home, who work through heat and rain, who put up the structures that shelter everyone else, and then return at the end of a 12-hour shift to somewhere that was never really designed for them. Bal Kumar Singh is 32. He is from Bihar. He is new to the city, doesn't know its streets, its neighborhoods, what it feels like to move through it as anything other than a worker.
अगर मजदूर ऐसा अगर घर में देखेगा तो फिर काम कैसे होगा? ठीक है, हम लोग तो ऐसे में रहते नहीं कि हम लोग को धूप में जाने से थोड़ा दिक्कत होगा। हम लोग को तो ऐसे ही घर में ही रहना है। शाम में थोड़ा हल्का फल्का गर्म लगता है तो मान लीजिए ठीक है, उससे काम चल जाता है, ऐसी जरूरत नहीं है। और बाकी सब ठीक।
He's not complaining. That's what makes it worth paying attention to. He simply accepted conditions that no one should have to accept. India's construction workforce, over 50 million strong, builds the cities we live in. But when the day ends, where do they go? Current worker housing meets the bare minimum requirement.
We are 12 third year students from diverse backgrounds architecture, psychology, and earth science, guided by an equally diverse faculty team. Presenting to you today are Nisha, Pragati, Varada, and I, Akshaya. We've partnered with Purvankara, Angiris, and Eco STP to shape and ground our design. To answer your second question, what did we learn? Project Weave houses 750 workers. Like Choti's Baba, predominantly male, with the exception of a few families hailing from all across India.
Tring tring. Baba, are you okay in the city? Everything here feels like it's fading. The river is getting darker every day, and I'm scared for the future. Is it grey and suffocating there, as they say?
No, Choti, if only you could see this. My home isn't bleak like a labor camp, it's so full of life. We work 9 to 5, some work overtime, and we take a lunch break at 1.
Baba, that sounds like a little colony. Living with so many people must be so much fun.
Yes, but it isn't like this everywhere. Construction worker housing is often overcrowded, prone to heat strokes, and lacking in hygiene, space, and privacy.
So, what makes your house different?
This site is located at Provident Equinox in Bangalore near Nice Road. Currently, 8,000 square meters of space is dedicated to the workers' housing, consisting of living quarters, a kitchen, dining area, toilet and baths, and an RO plant, among other facilities. It's primarily made up of puff panels and corrugated sheets. While this housing already meets basic needs, Team Knit aims to go further, creating not just a place to sleep, but one that fosters a healthier social environment. We've reshaped the site's boundary while keeping the total area and functions unchanged.
So, what did we design? Our modular housing starts with an entrance plaza that has the kitchen, dining, an open recreational space, a clinic, and a provision store. Bangalore reaches a peak temperature of around 34 degrees in May, with predominant winds being from the west and east. Our cluster arrangements has achieved an average thermal comfort of 92%, along with cross ventilation because of the staggered arrangements. Uh, we have provided optional crop cultivation options and an underground food storage cellar that allows for 7 days of food autonomy in cases of extreme emergency. On the eastern side, along each residential block, we have provided wash areas to ensure that the workers do not bring the construction site back into their homes. Downslope towards the west, we have the toilets and baths with a 1:10 user to fixture ratio, along with the laundry areas. Additional Additional services include the RO plant, a DG set, a battery unit, and solar panels that are accessed through the dining space. Finally, the entire site is bounded by a green intervention or a green buffer, which includes a 3-meter tall planting system of species with sticky leaves and large waxy plants to ensure that dust isn't brought into the site. This is a view of what our residential blocks look like. And this brings me to our unit design, which is a G+1 structure of 63 square meters, housing 12 people. That is 5.25 square meters per person, which meets the BOCW norms. At unit level, we have looked at thermal comfort using north and south shading calculations, where the front-facing chajjas are 1.1 meter and the back-facing chajjas are 1 meters. On the upper floor, we have provided louvers for the exit of hot air. Additionally, we have fan force ventilation, exhausts, and dehumidification panels. This is a view of what our upper floor looks like with the louvers and an arrangement of the storage and beds. When it comes to the cluster arrangement, here we dealt with it. We've dealt with the west and east shading devices using a 2.5 meter offset and fins. Arranging these clusters facing each other helped us create different sizes of community spaces and gardening areas. This also ensured the use of shared walls, minimizing the amount of material used because of the common framework. So here we see how there are different pockets of green spaces created with the cluster. And there's also the provision of a collapsible staircase on the side of each cluster that is shaded by a PET fabric.
Our primary building material is the RIX panel. It's composed of recycled plastic and demolition waste. In some places, it's modified with cavities to form jali-like fins, and it's also repurposed into paver blocks. The RIX panel doesn't require mortar, plastering, painting, or waterproofing, and is 83 to 91% less thermal conducive than cement or clay bricks. The unit is then capped with a lightweight roof of corrugated sheet and wood wool insulation.
Coming to our structural system, we have employed the concept of a weaving technique, where two L angles have been welded in a staggered configuration to create Z sections. These prevent the use of heavy I sections while achieving comparable structural strength using lighter members. Our main structural system includes sections that are a horizontal and vertical support of 14 to 14 to 5 L angles. The primary beams and columns are a composite Z section of 18 to 18 to 6 mm L angles, and the beams, which are the secondary beams, are composite T sections of the same L angles. We have also calculated the dead and live load on our structure and have achieved a max midspan deflection of 11.2 mm, which is as per the norms of IS 800 and 2007. The total assembly duration span for us takes 3 to 4 days per unit, given 6 members work on it, with additional 6 members working on ancillary spaces and services. Disassembly takes around 1 to 2 days. Our entire structure sits on a foundation system, that is the pyre foundation or the barrel foundation. This is a low impact system requiring minimum excavation. It includes the use of recycled drums with compacted aggregate material that act as point load transfers. These have a contact pressure of 107 kilonewton per meter square, with our SBC being 130 kilonewton per meter square, hence meeting the demands. We have also done a wind load test on our structure, that is with the foundation and also the uplift from the western side where we have heavier winds, and have achieved a factor of safety of 14.3. Coming to the details of our framework itself, we have the corner joinery detail, which is also our component model. We've shown how the column is attached to the beams and how the panel sits
at the column using MS flats, and the panels itself are attached to each other using tongue and groove mechanisms. We also have a beam to column joinery detail, and the staircase, which is the collapsible staircase, is fixed at the ground using a small compacted footing pad. And at the top, we have the landing getting attached to the balcony space using brackets. This is the roof system. We have two details. One is the vertical support that attaches to the roof panels itself, and the same vertical support that is attached to the wall below, along with the gutter detail.
Without any dehumidification treatment, the indoor relative humidity rises to 95%, intolerable for human living. To solve this, we introduced the 25 thick dehumidification panel made of naturally hygroscopic materials like sodium bentonite with brick dust, multani mitti, and jute fiber. Installed with a 25 air gap from the wall, it brings the overall relative humidity down to 60 to 65%.
Coming to affordability. At first glance, our proposed case seems more expensive than our base case. The base case costs an estimate of 9,795 rupees per square meter, while our proposed case costs an estimate of 12,856 rupees per square meter. So the question is, why did we choose to ignore the lower cost and instead we chose to optimize the life cycle value? Temporary construction housing worker housing is meant to be cheap today but more expensive to maintain tomorrow. So the real question is not how much does it cost today, but how much value will we create over time? As we know, time is money. When we broke it down to a smaller scale, a human scale, we realized that dignity costs only 12 rupees. Though our base case may perform well in the initial costs, we see that our proposed case costs, life cycle cost, performance, structural performance, efficient stability, and sustainability is much more. We also looked at multiple tangible and intangible elements such as thermal comfort, social cohesion, psychological well-being, and community spaces. Life at Project Weave is much more whole. We try to break down the annual maintenance and utility maintenance between our base case and proposed case. Our proposed case is 50% less. And when we looked at replacement costs, in the base case, there is a recurring capex of 23 million INR. This is due to material failure. In our proposed case, we have totally reduced this. So at the end of 25 years, our base case has a total expenditure of 117 million INR, but our proposed case has only 74 million INR. This is a huge difference, and we save 40 million over the years. Finally, when we looked at materiality, we realized that normal construction worker housing uses local materials which have a high embodied carbon. Our proposed case uses materials with low carbon emission. Our material Wix is sourced from a site 10 kilometers away, which is in Kumbhalkot. This reduces transmission emissions as well as removes waste from landfills. We also use a flooring which has a less carbon emission, which acts as a carbon sink. We also tried to break down the carbon emissions on a smaller scale. This table demonstrates that it's not due to one big impact we can create a change. It's multiple small changes we had to create that was able to achieve this large impact. For example, the structure we switched from virgin steel to EAF steel, leading to a 67 reduction in carbon emissions. For the flooring, the fiber cement and plywood helped reduce it to a carbon negative. For roof, the puff panel was switched to wood wool insulation, leading to a 94% reduction in carbon emissions. And finally, in our wall, the GI corrugated sheets were replaced with Wix panels, leading to a 93% reduction in carbon emissions. And these are only fewer highlights.
Moving on to energy strategies adopted in our construction worker housing project, our objective was not only to reduce energy consumption, but also move towards a net zero community. We began by improving the building envelope as it has a direct impact on the Energy Performance Index or the EPI. For foundation, conventional PCC foundation has a U value ranging from 1.5 to 3 watts per meter square Kelvin, while the proposed design, we have given pyre foundation, which gives an air gap which reduces the ground to ground heat transfer. Walls, a conventional wall will have a U value from between 1.8 to 8 watts per meter square. Our current hollow brick panel reduces this significantly to 0.12 watts per meter square. Roofs. Uninsulated metal roofs increase the heat gain and cooling demand, while our wood wool insulation roofs reduce the U value to 0.29 watts per meter square. We have given additional wall to window to wall ratio increase, which is from 8% to 12%. Additional strategies used are north and south orientation and mutual shading devices for solar exposure, five-star BEE rated equipments, biogas in the kitchen, and dehumidification panels. To support the original energy demand, we proposed a solar photo PV system. The community's total energy demand is approximately 212.3 kilowatts hours per day. This demand is met through 84 bifacial 650 watt TOPCon solar panels installed over 260 meters square, generating around 225 kilowatts daily. The system is backed by 20 lithium batteries with a 192 kilowatt storage capacity. As a result, the project achieves a net zero energy balance with a gross EPI reduction of 14 kilowatt hour per square meter per year, earning a 5-star BEE rating and a net EPI of minus 0.87 kilowatt per hour. Coming to water management, our goal was to create a circular system where water is conserved, treated, and reused within the site. The water balance diagram here demonstrates how every drop is utilized efficiently by giving aerated sinks and dual flush systems, by giving community washcloth areas and utensil washing areas. We reduce the proposed water consumption from 90 liters per person per day to 65 liters per person per day, achieving an overall of 28% reduction in water use. The result is approximately 50 liters per person per day of grey and black water generated, which is then directed to the STP. Our monthly average water consumption is 14 lakh liters, while the STP treats around 11 lakh liters, allowing us to recycle 89% of the water used. Rainwater harvesting further contributes to around offsetting 10% of the monthly demand. During monsoon months of August, September, and October, we get a 3-month water autonomy due to rainwater harvesting and reuse. STP, designed for a population of 750 people, it treats around 60 to 75 KLD of wastewater through a low energy treatment process consisting of screening, settling, anaerobic treatment, fertilization, polishing, storage, and reuse. The treated water is then used to flushing and landscape irrigation, while the sludge generated is diverted to the biogas system, creating a closed loop water cycle.
Coming to our fifth and final question, why should you care? I like to end with where we began with Choti and her Baba. When Choti asked her Baba whether life in the city was crowded or unhealthy or unhygienic, she was actually asking about if the people who build our cities are cared for. Project Weave answers that question clearly through healthy homes, clean sanitation, vibrant communities, comfort living environments. Sustainability is not just about saving energy, water, or carbon. It's about improving lives. So, yes, Choti, your Baba is safe and happy here. And the people who are building our cities are finally at the center of sustainability and dignity. Thank you.
Thank you, team. That was a really entertaining presentation. And let's hear jury's comments and take questions from them. Monish, we'll start with you.
Hey guys, very good presentation. I want to straight jump into this one big claim and how I want to see how you guys have arrived at it. You spoke about 92% thermal comfort, right? And that is primarily coming because of the dehumidification panels that you have. So what are the kind of simulations that you run and how did you arrive at this number?
For the dehumidification panel,
And also the 92% thermal comfort hours. And it's also, yeah.
We ran it mostly through Climate Consultant and then used tools to figure out the thermal comfort hours
Can
to
we go back to
calculate.
the slides where you're talking about the thermal comfort?
Initially, we actually didn't have a really promising thermal comfort rate, but then we did two changes. One is we changed our roofing material, and the other change was that the tool that we were using took the baseline for thermal comfort as 23 to 28 degrees Celsius, except most of our temperatures were falling 21 point something something. So it gave us like a percentage of 53. But when we changed the baseline to 22 degrees Celsius to 28, all of a sudden our thermal comfort hours shot up, leading to the 92%.
So you mean just by adjusting the base, the bottom line, you are able to get the 92% comfort?
Yes, sir. It was only that 1 degree difference because most of our
What about the higher limit, upper limit?
the upper limit we weren't hitting because it's Bangalore and usually the temperatures were moderate. The lower limit was our yeah, and also
I think we calculated mostly for occupancy hours, which is predominantly from 6 p.m. to 6 a.m. So afternoon when it used to get hotter,
So that's the base case. So you did not consider
no.
the daytime.
We considered everything. That actually, if you take those hours, the comfort only those hours, the comfort hour actually falls a little lower. So we did actually consider all hours. Sorry, our bad. But
No, yeah, you have to be very clear because when you're stating this, that's a big claim because if you're saying only the using usable hours, which is the evening, you should state that.
No,
That is
sir.
where it is. And if it is during the day, because this is a big claim. I mean,
Yeah.
especially if you're able to achieve it with passive means, 92%, that's like an ideal number. And in any
Yes.
climatic conditions, right? And uh, the simulations and everything that you're running, right? This in the presentation that really doesn't show, especially when you're talking about a passive building. The two things that you need to talk about, especially when it comes to thermal comfort, one is the cross ventilation and air exchanges and how the airflow that is being circulated inside the space. And you also spoke about this hybrid system of dehumidification. Can you go to that, please? Okay, so have is this being tested and deployed?
Yeah.
This
Yeah. So we did multiple tests with different compositions using these same materials, and we started varying the ratio. So sodium bentonite is a strong
so
water.
is this your own recipe?
It's
Lovely, fantastic.
So yeah, there are different samples there where we use different sort of like coconut coils, jute fibers, vary the ratios. So we tried looking at the calculations. So for a room, we took the occupancy and the leakage of relative humidity and everything, and we realized per day it's about 5 liters of humidity release, and that's what the tiles have to absorb. So we designed 20 tiles for one room, and each tile would absorb around 200 grams of water. So this test tile is about 1/10 of one tile, and we did this using a simulation, like a room simulation, where we had humidity, and then we checked with the hygrometer about the absorption and things like that. So yeah, this is
That's great. I mean, so one last question and then pass it on.
Yeah.
So this is because these two claims are interconnected. You're talking about thermal comfort and the humidity.
Yes.
They go hand in hand. And if what you're talking about is right, great experiments. If it is not something that is already been deployed, kudos to you for actually trying out something.
Thank
You should also consider the regeneration time. For whenever you're talking about dehumidification with any material, it is absorbing moisture. Then it has to release, and then
Yeah.
there is a time factor.
Yeah, so we have a regeneration period of 7 days. So every 7 days, suppose they're on a Sunday, they go and keep the panels out in the sun for about 3 to 4 hours. So it's regenerated.
So you need to mention, like I think, especially when with such big claims, you need to talk about the the values where you're considering thermal comfort and also these parameters.
Yes, sir.
Okay.
Thank you.
Thanks.
Team, good storyline you had from the beginning till the end. You kept the thread, so I think that was something nice. I like that. You also introduced all yourselves at the beginning. It's a nice thing to do whenever we have a group presentation. And I also noted that you have a better window wall ratio compared to most sort of housing in this kind of category. It can be better, but yours was, I think, close to 15% or something. So yeah, that also matters. Um, Something fundamental I want to ask you is that you've done a modular system, you've done material swap, and in the beginning you started with 5 questions. So what's your biggest learning? Not what you told as part of this presentation. But what have you learned looking, I mean, after going through all this process and now that you have the proposal that you have?
I think our biggest takeaway is that there are so many things available to us if we research, but we also realize that everything comes at a cost. So if it's not like if a real person cannot use it in terms of money or in terms of availability, no matter how great the idea is, I just don't think it would work. So we tried considering all these things to make it like really workable. So having like a thorough all-round sort of effect and like something that people can use and actually build with the values. I think that was our takeaway.
Okay, all right. You also did an interview of some of the construction workers, etc. So, do you think if we were to, this is a similar question to the previous team that I'm asking you, if we swap the material back to bricks in your design scheme, will it still be a good proposal or not?
In our case, no, because bricks has a much higher life cycle time. So the bricks panel would last at least 30 years before you have to replace them. So that itself, as well as we did a comparison cost, like the bricks company, Angiras, has done a comparison cost between like normal bricks and cement blocks. And the cost is also reduced, as well as it's waste, it's reusing wastes as well. And the carbon emissions is much less.
What about a sense of space and livability? Will that change or is it the same as a living experience? Because everyone noticed that living experience is really bad and that's what you set out to make better. So I'm asking that if I have to swap your material back with bricks, will it degrade or like meaning will there be no improvement in living experience or will it still be way better?
I think it'll still be way better because our material is it's something very clean and like low maintenance, and then just the fact that of having like a clean wall or a clean surface, I think it definitely adds.
Also, Rix told us that we have the option of having a finish, like a paint finish on the panels. So if it's something we haven't, yeah, aesthetically, it's something we can consider looking at if it's because I know that the one we have here is a dark panel, but ideally we would like have a finish on it.
I thought I was hoping for you to talk more about your spaces and things like that. Anyways, you can think about it.
Unit design was actually based on the measurements of this panel. So a lot of the positive points about window wall ratio all basically derived from the Rix panel. And as far as spatiality goes, again, like the transportation is very simple. So you could, yeah. Oh, also it reflects quite a bit of light, daylighting. So
Okay. Let's go to your slide where you had puff panel. You had a comparison between proposed design, current design.
Yes.
Yes, this one. Can you go full screen? And also the slide before this. Okay, so you can stay here. So this roof, you're saying current site condition, that is what the project partner has?
Yes.
Does that what it means?
Yes.
Okay. So they do have a puff panel in the roof.
Yes, they do.
You also have the same proposal.
No, we are giving a wood wool roofing system. Error, yeah. We changed, yes. Error, yes.
Okay. So you have a better insulation.
Yes.
Wood wool.
Wood wool, yes.
Okay. And the cement board which they're using for wall, you've given it for your floor, isn't it? Okay.
So our floorboard, our flooring is a BWR plywood with epoxy layer and FR plywood shuttering as well.
Okay, so
So it's
then
a
let's go to
composite
the previous slide. Yeah. This one. The floor element here is a fiber cement plywood. Is that what you were trying to?
Fiber cement is the base case, plywood is our case.
I see. So plywood is carbon negative?
Yes.
How is it?
So we again plywood is a bio carcinogenic material. So throughout the lifespan of the tree, it absorbs much more carbon, and we considered the emissions of when it's processed and the entire thing is created, and it's still much more negative.
Is
So
this
that's
something
why.
you calculated or the manufacturer gave you the
No, this is something
information?
we calculated. I mean, as in we looked at the different materials, we had values, and then we checked the overall, as in if it were to work together as a whole component, how would it work? So we realized that it is carbon negative.
This is very interesting. I've never been able to reconcile with the fact that it can go negative. Anyway, so that was one. And the dehumidification panel, it's indoors or
Yeah,
outdoors?
indoors, indoors.
Okay. All right. I'll pass it on. If there's some time, then I can add.
Let's go to the structures slide. First we'll go to the plan. We'll just go to the architecture plan. So these are series of blocks, right? These are. Can you just go to the plan where you had shown that stagger planning on plan? Yeah, yeah. So what was the reason of staggering this build farm?
The stagger was for shading. So on the east and west side, for the shading is why we did the stagger. And while considering the stagger, we also made sure that the way the framework sits, the same components can be transferred onto the subsequent units.
Okay, since we are staggering, I think the support location creates a problem, right? So now, what are the vertical supports? Is it a Z section or is it a
It's a Z
it's a
section.
T section?
Z section. No, no, no. It's not.
Then I think what is the reason of using Z section? Are you shifting the walls for different areas? Say,
Yes, we will be.
is there any detail? Is there something to show me?
Shifting.
No, just show it. Yeah, just this. Yeah, just keep it. Just keep it there. Just keep it there. Don't show it on the plan actually. On the plan, yeah, on the plan, like, see what is happening here since you shift this whole building, okay, with Z section, one wall becomes part of the two spaces and the other wall becomes an exterior. So how does the wall shift? You got it what I'm saying is?
So can you?
Correct. No? So it is on one side of this Z section.
Yeah.
When when it becomes external, are you putting the wall on the outside?
No, I think the
You understood what I'm saying?
yeah, the panel sits mostly on the beam, right? So the beam is a T section, so it's able to sit on that.
So this is Z.
Yeah,
okay,
that is
Z is made up of two angles.
Yeah.
Okay, T is also made up of two angles. So you get two flanges.
Mm-hmm.
In the column, you have one flange this
Yeah.
side, one flange that side. So it gets a socket. It gets a socket where the panel can
Yeah.
go. So if it is the external section, the wall is on the outside.
Yes, the
If
wall
it is
is-
on the internal, it's is on the same stage or it goes inside.
It'll be on the inside and on the exterior wall, it'll be on the outside.
So
Okay.
yeah, so I think is there a particular reason why you have taken Z section?
So it was
Why?
just for I think comparatively, if you took something that's an I section, it would be a larger member, and Z section helped us create smaller members while carrying the load. That's why we went with the, and also when it comes to fitting of the panels.
Okay.
Yeah.
Okay. So this same Z section goes on the top for the roof.
Yeah.
It goes on the top.
Yeah, we have Z purlins on top.
Z purlins. The same columns will go, no? Can you just show? Is there anything?
Back.
Just show the view. I think ideally, this Z section is a purlin that doesn't have any relation to the column. Correct, na? As per your cross section, right? Yeah. And okay. Oh, this is the, acha, this is, I can see there. Yeah, these are the columns.
Yeah.
Then the floor doesn't have any members.
The
Floor has
floor
a
also has members. We have
floor.
beams. Yeah, yeah, yeah.
So what are these horizontal members which I see? Even though you are doing this panel, every panel has a horizontal member, is it? Which is a tie.
It was just for support. Yeah. Uh, yeah.
But the panel itself can span between two Z sections.
Panel sizes are 800 into 900.
So panels are, see, it's like depth is less, length is more. Panel, right?
Yes. Yeah.
So it sits one above the other.
Mm.
So at every point you have put a structural member, is it? That's why I see structural member horizontally.
Yes, we have. On the outside, we put the structural members so that the joinery isn't exposed. So if there's rain, then it doesn't get in through the
So
joineries.
if you
That's why.
put horizontal planes, how do you handle the door?
The door?
Yeah. If you have to have, are you cutting the panel to make a door?
It's not there on the smaller. So the smaller ends of our building don't have these. The larger. And the way the Rick's
No,
panel has
what I'm
been.
saying is you are doing panels like this, right?
Yeah.
Between the Z
Yeah.
section. So imagine the panel, the column to column spacing is how much? 8 feet, 9 feet. Now this one, verticals. What is the spacing between the columns?
2 meters. Yeah. 2 meters. Yeah.
2 meters.
Yeah.
The door is not 2 meters, right?
No.
You don't have doors on that direction.
We don't have doors on that direction. No.
You
Yeah.
don't have doors
Yeah.
on that
No.
direction. So when it comes on the front, that also is horizontal, as I could see.
The way the door has been, the width of the door is technically the width of the panel that's used here. So if you just remove that area of the panel, the
No,
large.
you understand. You understand here. When you look at the door, okay, even though the panel is horizontal, the panel get cut half without a support. So as per your drawing, every door also should have a Z section.
Okay.
Correct, no?
Yeah. Okay. Yeah.
Correct?
Okay.
Okay. So when you are doing these panels horizontal, you don't require a tie. Okay, that itself will tie.
Yeah,
Okay. Otherwise, it becomes a hindrance for you. You can't put the last member.
Yeah.
Because two sections are put, how do you insert it? Okay. So is there a prefab? Is there a system which you have done prefab on this?
The Rick's panel will be a prefab system. Right now, Rick's comes in the form of like a normal brick system, but with our proposal is that we
With the
make
columns. No, prefab in what I meant is the skeleton. Because when I look at your skeleton, you just go back to the analysis what you have done. It looks very like a mesh. But when I see this construction, it doesn't look like a mesh. Can you just go to the analysis?
the load.
No, I saw the skeleton, no, skeletal with stresses. Yeah, look at that, yeah. So it looks like well connected, no, everything, every line is connected. So in that, the column is connected to your purlin. Huh? But when I look at your drawing, it is not connected. The column is not connected. So what I am saying is, there has to be some truth, no? Huh? Your architectural section should reflect what you have analyzed. You can't have two drawings separate, and you can't force me to accept it. Correct? That is one thing. That clarity is very important. Okay, you can't just put, abrupt two images which doesn't match. Okay, architecture and structure is seamless. One is visible, the other one is invisible, which needs to be perceived. But when you remove and I see it, it has to be correct. Okay, clear? Second thing, go to the foundation. Yeah, look at this foundation. It's out of scale. No? What is your column? Where is the bolt? What is the size of the bolt? Your anchors. The scale is 1 in 25. Big scale of foundation. But your column and then bolt is like as though it is like screwed. You need to put one bolt though nicely. But if this is what you need to understand. Okay. Clear? And the bolts are gone so out to the plates.
I think there's something wrong with this kid. What are you trying to say? Look at the chemistry.
Yeah, you got it, na? So if you can, I'm just telling you, you need to understand. Yeah, there's something wrong, and then you show it. There is one guy, maybe an engineer. He will say, "What the hell is this? Huh? How much marks did you give?" They will ask us.
Mhm.
Correct, no? Huh? So what I'm saying is, you need to be more responsible, but good work. But take one more detail, no? Structure, one nice skeleton you can take. Okay. Yeah, thank you.
Thank you, jury members. Thank you, Team Net. So now let's take 5 minutes and get ready for the next presentation. Okay. Hi everyone. Our final presentation is from Team Shramodaya. They have worked on a project called as Sahajivana, which is located in Saswad, Pune. So team, you will have 20 minutes to present your work to the jury. At 15 minutes, I'll ring a signal like this. Okay. You won't have a 21st minutes and I'll ask you to stop at the end of 20th minute. Okay. After that, 10 minutes for Q&A session. Please keep your answers direct to the point and all the best. Okay, ready? Your time starts now.
I'm a worker. I build cities, skyscrapers, and roads that shape the future. Yet, I return home to a tin shed without proper sanitation, utilities, or dignified living conditions. My children grow up in the same environment, suffering. This is the reality of millions of workers in this country. Good evening, respected jury, SDI officials, industry partners, fellow teams, and our dear guests. We are Team Shramodaya, and today we are here to present the solution for this problem. Let's begin with a short video.
With every rising sun, our cities keep growing. New building rises, roads expand, and infrastructure spread to support urban life. The construction industry contributes 9 to 10% to India's GDP and employs over 50 million workers. Yet 60 to 70% are migrant laborers. Team Shramodaya visited multiple construction worker housing sites and interacted with workers to learn about their living conditions. A small tin shade room where an entire family lives. The roof is low, the space is cramped, and a single dim bulb struggles to light the room. Cooking, sleeping, studying, everything happens in the same space. Even the most basic services here comes with heavy challenges. Temporary electric connections, rising energy costs, and fragile infrastructure struggling to support daily life.
पापा सबके लिए घर बनाते हैं पर क्या हमारे लिए भी कोई घर बनाएगा
हम करेंगे.
To turn this question into action, Team Shramoday came together, a collaborative group of 9 civil engineers, 1 electrical engineer, and 5 architects, guided by a faculty advisor and united by one vision.
After understanding the challenges faced by the construction worker, our next objective was to create a solution that is sustainable, also practical enough to be adopted by construction industry. That vision became Sahajivana. Sahajivana meaning living together. It is a modular net zero ecosystem designed to improve worker well-being through sustainable living, digital safety, and rapid deployability. From the very beginning, we know that solving this problem required the right industry ecosystem, not just the right design. That is why our first strategic collaboration was with Credai Pune Metro, which gave access to the India's leading developers, which helped us connect with the two developers named Vascon and one is Rajpath. Rajpath Infracon represents linear infrastructure projects such as highway, while Vascon Engineers represents the building construction. By studying both, we were able to compare two different housing conditions. We strategically onboarded domain experts to address each challenges. Scrapshala strengthened our circular economy approach. Aquatron enabled our decentralized water management. Shriman EcoCycles contributed recycled plastic construction materials, ensuring that every major aspect of Sahajivana was backed by an industry expert. Through multiple site visits, interactions with the workers, interaction with the site managers, one observation became very clear. While both sectors face worker housing challenges, highway construction projects are significantly more demanding as the entire labor camp needs to be shifted and to relocate continuously with the progress of the road. Through multiple site visits, this made Rajpath project at Saswat Pune the ideal site for our proposal, spread across nearly 10,000 square meters with temperature ranging from 16 degrees Celsius to 40 degrees Celsius. This site provided us with the perfect opportunity to design and validate a truly relocatable worker housing system under the real project conditions. These collaborations helped us to transform site observations into measurable outcomes, enabling Sahajivana to achieve an EPI index of 13.98 kilowatt per square meter per year, representing a 54% reduction compared to the conventional baseline. Every collaboration and every site observation shaped our design decision. Let us now show you how these design insights evolved into architectural planning of Sahajivana.
The site has three distinct user groups: bachelors, couples, and family users with different spatial and social needs. All residential units uh, face inwards towards a common segregating kitchen and dining combined space. The form began as a simple stepped mass inspired by the site's contours. Instead of fighting the land, we chose to build with it. The mass was then broken into smaller clusters, creating courtyards that encourage interaction. The final form is therefore not just shaped by the contours, it is shaped by the community that helped create. The climate responsiveness was another key driver. Analyzing the wind patterns of Saswat, Pune, we rotated our site 15 degrees, which helped it aligning with the prevailing southwest winds, which thereby created natural wind corridors. The project steps gently across three different levels, 0, 3, and 6 meters, following the natural contours. This approach reduces excavation, preserves the site's natural character, and creates a built environment that feels rooted to the tech landscape. Different units are placed in different levels, giving each group its own identity. The, the bachelor unit shares a common washroom, while the couple and family units share another washroom. Running through the center of the whole design is a kitchen plus dining space, which doubles up as a OET, which can be used as a dining space, a skill development workshop, and for children's learning. Separate pedestrian and vehicular entries reduce conflicts. The office is strategically placed near the entrance for efficient management, which does not disturb residential life. Supporting facilities include biogas plant, site circular economy, which manage waste sustainably. Together, the project becomes more than a building. It becomes a self-sustaining unit. The furniture in interior units are made from recycled tires, wood, and rope, which reduces waste, lowers down cost, and provides durable and multifunctional furnishings. The traditional woven rope cart adapts to the body's natural contours, providing ergonomic support and improved rest and recovery for construction workers after long working hours. Bachelor units consist of majority of the user group, which is observed in both our companies, Rajpath and Vascon. They have a total of 204 workers, constituting of almost 85% of the whole user distribution. Then comes the family units. They are 25 in total, each accommodating 2 parents and 2 children. The unit includes a study table, a chair, and a sufficient shelving for storage facility. Couple unit, couple unit 9 in total are located at the farther end of the site, which results in greater privacy, reduced noise distraction, and a more peaceful living environment. The courtyard is a calm, shaded space for gathering on every day. During festival and celebration, it transforms into a vibrant community space through temporary bamboo structures and flexible use. From economical perspective, contoured land on the outskirts are often undervalued, and most developers avoid the complexity of building on them. This results in significant lower land cost. By our design, we reduced excavation, filling, and site preparation costs, making the project more cost friendly from the very beginning. Even the water follows the same philosophy. The contours naturally guide the storm water through bioswales and landscape elements.
So this is hello. This video signifies the sequence of the various elements while framing the housing unit. So this is the exploded view of all the elements which is to be fitted on the structural frame, which consists of. So first it consists of the wall panels. Wall panels consist of the plastic frames, which is which is used of recycled plastic. There are two recycled plastic frames which are installed in this system. Inside the two panels, the air cavity is installed with the recycled steel column. Next, the joiner details is that two-way, three-way, four-way junctions are used to join the structural frames into one another. Roof specification is like corrugated RFE sheet is provided at the top, spacer frame is provided in the middle, and the linoleum sheet is provided at the bottom. So we know that low U value on envelope improves the thermal comfort. So the our wall, which is made up of plastic, which has U value of 0.28, floor has U value of 1.03, roof has U value of 0.19. Also, the reflective roofing minimizes the solar heat gain. Air cavities enhance thermal insulation performance. Lightweight modular system enables the rapid construction, as well as the recycled and reclaimed materials support the sustainable design. So next is GeoGrip pile foundation. The GeoGrip root pile system uses helical screw piles that are rotated into soil without excavation or concreting. The helical plates provide bearing resistance while pile shaft develops friction through the surrounding soils, allowing loads to transfer safely to the ground. The GeoGrip pile foundation has a factor of safety of 6.2, and this ensures the structural stability while enabling the rapid installation with minimal excavation and full reusability, making it is an ideal solution. So this is the rapid root pile. It is made up of aluminum, and these pipes are dug into the ground by drilling. Next.
While GeoGrip Pile solved one of our biggest issues and challenges, we soon realized that sustainability cannot stop at the building itself. A truly sustainable worker settlement must rethink everything that happens around the building. So these things led us with the three innovative strategies and our designs or some innovations. So during our visit to construction site, every day we found out that large quantity of waste is generated, and at the same time a large amount of new materials has been procured. So in simple terms, one end of the site was generating the waste and the other end was purchasing new materials for the additional stuffs. We believed that these two ends must be connected. So to make this possible, we collaborated with Scrap Shala with the sustainability expert Ms. Shika Shah to establish our site circular economy hub. Instead of treating construction waste at the end of its life cycle, which transformed it into the beginning of the another. So additionally, after this, we found out one major challenges at the construction site that was related to the modularity and mobility of the electric poles. So one of the lessons we learned throughout our journey is that innovation does not always mean that to innovate something completely in a new way. Sometimes it also means that redesigning an existing solution to solve a problem that everyone has accepted for the years. Solar powered streetlight already exist, but they were never designed for temporary construction sites. The challenge was not lighting, the challenge was mobility. Highway construction project continuously progresses, forcing labor camps to relocate every few months. Transporting conventional 6-meter light pole is difficult, expensive, and inefficient. So instead of reinventing a new street light, we redesigned it for mobility. Lumora introduces a telescopic modular pole that collapses during transportation and extends during deployment, making its relocation significantly faster, safer, and more economical. Combined with our reusable GeoGrip foundation, the entire system can be installed, dismantled, and relocated without excavation, concrete, and or any curing time. Once deployed, integrated solar panels make Lumora self-sufficient by powering both the lighting system and the CCTV surveillance mounted on the top. The CCTV surveillance is compliant with our new innovation known as Nexvora. It is basically a AI-powered monitoring system which enables the great accuracy with identifying the possible. Before that, I'll share during our site visit, we observed many challenges, but that some of the challenges were not related to the infrastructure. Some of the challenges were like we are providing the dustbins to the laborers, but they are not using that. They are throwing the waste outside the dustbin. So we are trying to develop a AI model which will detect the threats or detect the violations, and that will send the violations to the supervisors, and this will act as an app which will look after it. So Uh, Recognizing that artificial intelligence requires specialized expertise, we strategically collaborated with a student team working in AI and computer vision. While we developed the problem statement, operational overflow, and the real world application, they are helping us to transform this vision into a functional digital platform.
The problem was excessive heat exposure, majorly through roof. To address this, we introduced reflective slope roof, shaded walkways, and chhajjas, which reduced our heating exposure to 60 to 70%. Many a times, some units do not receive adequate daylight, so we optimize of openings in such a way that they have enough lighting and reduced glare. The integration of simple yet passive design strategies such as slope roof and central courtyard help our design be more efficient. Poor airflow leads to unhealthy and indoor environments. So we provided 6 to 8 ACH and less than 1000 carbon dioxide ppm.
Let's come to the energy performance. So the ideology behind the energy performance, what we have done here is to get the best out of the site. We two things which we needed from our energy part from our collaborator. One was that they needed a transportable energy module, and second thing was very simple and it should be resilient. What we did was we put transportability and central design as our core motto. As you can see here, this is our kitchen. The kitchen roof panels are installed on the kitchen roof. This is a 24 kilowatt site, and we have replaced our diesel generators, the baseline diesel generators, with the 24 kilowatt site. So let me talk about the baseline. We had two 120 kVA generators running 24/7, and which was costing us 10 lakh rupees a year for diesel. The primary cost was 28 lakhs, and our solution costs 13 lakh 90,000. What we have done is we have reduced our EPI from 35 plus kilowatt square meter a year to 13.98. How have we done that? Let's talk on the next slide. Our primary source of fuel is diesel on the baseline, and on the proposed one, it's 100% solar. The payback period is 2 years. So this is what you have done. Used BLDC, used energy efficient lamps, bulbs, have integrated integrated renewable energy everywhere possible. This is a future scope. We have integrated the Lumora model along with vortex turbines. We have discom credit system, a bank system where the discom pays you with the credits. The more units you generate, this is a net positive site for energy, and it has seasonal balancing.
So about water performance, we have a few performance objectives: 35 to 50% of fresh water reduction, 90% of wastewater recycling, zero energy, and AI monitoring. So this is the calculation of water demand: 22,500 water per day, liters of water per day. So this is the flowchart of the water from source to uses and up to recycling. This is the water consumption chart, and it signifies the yearly distribution of water and its uses and consumption. So this is the monthly consumption, and it signifies the rainwater harvested, grey water reused, and black water treated. Next is water efficient. These are some water efficient strategies which are used to enhance the water treatment and water reuse. So this is the consumption chart of the water. So grey water and black water. So this is the wetland system for grey water treatments. It has 5 stages. It treats the water, and we can reuse the water in flushes. These are the bioswales where the stormwater management is done. It reduces the peak runoff flow by 20 to 70%, reduces the runoff volume up to 80%. Aquatron is used to which separates the urine or water from solids, and it is a bio chamber filtration for reuse, and the water is used for flushing. This is a practical application of the Aquatron.
coming to embodied carbon, we have reduced our embodied carbon 72%. This is the baseline. These are the conventional but non-efficient materials. We have considered these materials as our go-to materials. We have used bamboo wherever possible, and we have used reclaimed wood, recycled wood, and recycled sheets, recycled steel frames. We have also used a linoleum sheet, which is nothing but natural, biodegradable sheet. This is the performance. We have the roof has the highest reduction. We have reduced practically 100%.
Thank you, Team Shamadya. You gave a very insightful presentation. But that was the time. So now let's hear jury's comments and take questions from them. Deepa, over to you.
Team Shramodaya, good energy in your presentation all through. It was also fast paced, yet you ran out of time. So it could have been planned better. Um, and the video in the beginning, I think it was a good way to capture the problem, the lay of the land when it comes to construction workers and the housing. Yeah. Um, so some of my questions are, I felt that some of the numbers were very optimistic. For example, the wall U value of 0.28, like this is a section.
Yes.
Yeah?
0.28 or 0.18?
0.28, I think. So I know there are two boards, but this is very optimistic. I don't think you'll get this low U value for this kind of an assembly. It has an air gap here and a steel section. The members inside, and the board is quite thin for the kind of U value you are claiming to have calculated. Yeah, 0.19 is the roof. That also doesn't have any insulation. It is just the air gap. Air gap does insulate, but it depends on the size of it. But this uh, is very, very low for your section that you have. Is this a manual calculation? How did you calculate this?
These were calculated layer by layer, and we just summed them up. So the materials, this was a composite. So what we did was we tried to find a material similar to this, and then we calculate the U value.
So what's a material similar to this?
Actually, the plastic in itself, it has a very low U value, and the air gap enhances the U value, reduction of U value, and by the research based only, we have finalized this value at the.
So the plastic is part of the final design. We thought just to hold it right now. Yes.
On the top, no, it is not. It is only for finishing purpose. Yes. It is only for finishing purpose. The final design, it is on the linoleum sheet. It is at the final, at the top.
This really needs another review, so you may want to recheck your the assumed values to begin with.
Okay.
Okay. And then, looking at your design, you have very small windows to the size of your room, and then you are saying you will have 6 air changes per hour. It's naturally ventilated and it's super well lit. Those all seem to be very, very optimistic for the size of the windows you have to the room and the number of occupants, high density, which it is.
No, we actually revised the window size. The front window size is of 1 meter by 1.2 meter. The rear side, that is the back side, is 3 into 1.2 meter. We actually revised the window sizes later on. So that gives us enough ACH to go ahead with. Yeah. Front 1.2 and rear is 3 into 1.2 meter.
So what is the size here that you have? This is not revised, correct? This is your older section, correct?
Yeah, this is the older
So
section.
what is the size here?
Here the size is 800 by 1 meter on both sides.
Okay, so 0.8 by 1, and you've increased it to 3 meter by 1 meter.
Yeah, on the back side.
Yeah. Okay. Um, I still feel this is a lot of air changes that you're getting, and you will never get a steady air change in a naturally ventilated situation because it is dynamic, right? So you may always, like the range, you have a range, this itself is very high. It could go as low as 1 or 2 also. To
This
say
is
that
just
your lower end is at 6 is very optimistic. Okay, so you really need to do some more inspection to actually see how much you are getting through various times in the day, and so on. And also, if you assume that in the daytime it's not occupied, but then maybe it's closed. I don't know what is your assumption, but if it's closed and heat gets built up, so, and in the night time, then you're assuming it's open. So all of those things has to be thought through, and then the basis has to be clarified, and then you have to come up with what looks like a reasonable, and then the CO2 and all of that is much later.
Yeah, right,
Yeah.
right.
So it needs some resolution. Another question is, this is quite interesting. This whole solar, Lumora and the other app that you mentioned. I think it's had good potential to develop into something uh, better. And you said that the construction worker, the whole housing is very mobile, given that they are also working on infra projects, right? So with that, I would say, how did you assume that the DG is running all through the year? Is that a reality in your baseline?
So the DG on the particular site we are right now, it operates for 300 days a year.
Why so? Is it
Because
off grid?
yeah, it is off grid. It runs on diesel. It is a Kirloskar 120 kVA DG set.
You're saying that there is no connection to electricity on the
It's a
site.
diesel generator, so it runs on diesel and it gives electricity. So it's basically it is like a small gen set.
I understand. You are not connected to the grid at all. You have to depend
No.
on the generator.
Yes. It's totally diesel dependent.
So you are saying you have connected your solar to the grid.
Yes.
How is that
So
happening?
I'll explain. The reason they are not connected to the grid right now is because they thought cost feasibility 5 lakh rupees for 3 years was a bit high. But when we pitched the solar, they found out that they can just add up the credit bank system. They can use it to their advantage. So basically, you pay once. What we did was
No, yeah, wait. You're saying that it's cheaper to run your diesel generator than to be connected to the grid to begin with?
the diesel generator is expensive, but it is accessible only in remote locations where the grid cannot reach. But when we propose a on-grid solar system, the discom is forced to actually provide you a connection there, since you are a provider. You're feeding back to the grid.
I understand. So you're only for making a comparative case, you're considering DG.
No, this is the actual real site scenario. They actually implemented the on-grid solution because of us when we pitched it.
How is it possible?
You can give us some comparison in rate. You are saying you took solar,
Yes.
then you will use it to put it to the grid.
You can get credits. That's not a problem.
Yes.
Why is it that you're connecting the grid, I mean, the solar to the grid, and you don't want the building to be connected to the grid only?
Yeah, I get the question now. So the thing is, if we put our solar directly to our building, it will increase our storage costs. Now our storage costs are equivalent to almost our whole cost, the capital cost of the system. For 3 years, I don't need a battery pack which is huge enough to power a 24 kilowatt system, which will cost me 20 lakh
Isn't
rupees.
the first assumption that there is no connection to the grid possible?
No, that's not
That is not true.
No.
Okay.
Grid. When do these situations arise? When
So you are proposing, like, in the event of this being in a remote area, this is how it could
yes,
be.
yes. And we did consult one of MSCDCL's engineers for
And
this.
if you don't have access to grid, you have to have battery bank.
We have to have a battery bank, but if our system exceeds 20 kilowatt, the discom is forced to actually give you a grid connection.
I see.
Because we become a provider to the grid. We become like a mini generator to the grid. So we'll be providing to the grid. We won't be directly taking our own energy units generated.
Okay, I will stop here because I'm taking too much time. compared to, I mean, we have more questions coming in, but this, an area that is not clear.
I think, yeah, looking at the model, I think it's quite honest that the whole terrain is sloping, right?
Pardon, the whole?
The whole terrain is sloping in one direction, right? So what is on the other side? On the sloping side, what? Do you have a lake? To the bottom side, do you have a lake or something?
We have a road over there, and after some distance, we have a village over there.
Village, okay. So what I mean to say is, I don't see any retaining walls here.
Okay.
So when I look at this, even in your cross sections, or there's no cross section, but your visuals indicated that you don't have retaining walls to match the level differences, right? You have a building at the low level, you have a building at a higher level, right? And then the difference is not taken care by a retaining wall. You have just sloped the ground.
No, actually, to cater that, we have proposed that small bushes and small grasses will grow throughout the site, which will help avoiding soil erosion. So
Okay, that is
that's
an
what we done.
assumption, right?
Yeah.
That's an assumption.
Sorry?
That's an assumption.
No. We have provided.
Acha,
We have
so
proposed to provide.
so what is very important here is when you are anchoring foundation through this compression, yeah. So you feel that you need to have the soil confined all around. One side is confined, the other side there's a level difference, right? And the soil is not stiff; it is sloping down. You mean to say the grass will protect your foundation? No. So I think see what I'm saying is we can't assume a lot of things, right? So I think there has to be is this particular system what you're suggesting, is it okay for us, or should we go for level foundations? We need to have level foundations. So some of the areas where there's a level difference, probably the foundation which is coming on the edge should go down so that there's no settlement, right? Correct. Huh? So I think this is very critical. I don't mind to, I don't want to do the retaining wall, but I'll slope it. I'll protect it for protecting, no, I protect erosion through, turfing with grass. That's fine. That's fine. There's no problem. But what will happen to the foundation? That is one. Okay. Second thing is, I'm not very clear about the structure. What is this structure made up of? What is this? What is the basic structure? Is it steel structure? Is it wood structure? What is this?
So basically, the structure is made by the recycled steel sections.
Steel, no? It
Yeah,
is steel
steel.
section. Yeah, okay. Ah, so these
And
are anchors, aluminum anchors. Yeah, right.
yeah,
Yeah. So what is this whole thing is made up of? Is it
like
box sections?
yeah, box sections.
It's box sections.
Yes.
Okay, so the whole structure, ground plus one, is made up of skeletals of steel,
Yeah,
right? And then you have cladded with, you infilled with this
walls.
particular wall
Yeah.
system.
And that plastic is like food graded plastic, so it does not provide any issues after getting heated, any fumes and all. So that's safe for human, and it has been tested by the manufacturer with some
Okay.
fire ratings also, so
Okay.
that one fits best for our conditions.
What will happen to this electrostatic force because of the plastic?
Okay, we have not thought about it yet.
That is quite
Yes, yeah,
dangerous, no? That is the force which emits.
yeah, we'll look onto it.
Yeah. Okay, that's it. Yeah.
But there's one more thing. Actually, every joint and every part of the beam is being grounded directly with a actual earthing pit. So we can actually drain the voltage generated in an electrostatic force.
Okay.
So yeah,
The electricity generated by this electrostatic force, is it?
yeah. So every
It
part of the structure is grounded.
okay. Anyway, just yeah.
Hey guys, it's nice to see a lot of enthusiasm towards using a lot of these modern systems, AI technology. Great. I think you guys try to incorporate a lot of these new technologies and materials that are coming in. I think that is commendable because you wanted to test out new systems. So, but before getting into that, I have a few questions on that. I want to get back to the basics. What's the ground coverage of your? Any idea? Just a guess.
Approximately 2,300.
Ground coverage. What's the percentage?
Was a percentage. 20 to 30%.
Right,
Yeah.
20 to 30. 20 to 30 for a construction workers housing is a luxury. A
Okay.
standard house in the cities is approximately 50%.
So
Okay.
I'll
You can answer like everything in one go. I'll just very quickly run through my points because we already, I think, already taken a lot of time. And the second thing is the way you position the buildings in the master plan. A lot of buildings are on the edge of the contour, like at least I don't know how the real contours are the way you have shown it, even in the sections. You cannot have the foundation. Otherwise, you have to, I mean, it's everything is possible, but then the length of your foundation and the excavation will go much deeper, increasing the cost. That brings us to the cost of the building. So you have used a lot of systems, no doubt about it. Like you spoke about the AI, all of these techniques and the steel construction techniques that we spoke about, the smart AI camp, supplying the solar panels and supplying to the grid. But your overall costing, you haven't reached that slide, is 6,000 rupees per square meter. You ran out of time before you reached that slide. Yeah, go back. One slide. Yeah, 6,000 rupees per square meter, which is 600 rupees per square feet. If this is a reality, you will, I mean, this is too good to be true. 600 rupees per square feet for a construction with so many systems with that kind of a spread and everything. So, like, even without actually glancing at a detail into the costing, this is way too off. Okay, that's something that you should be considering. Now, speaking about the factors that you spoke about, like all the systems. So like I said, it's really nice to see. I think I also had the same question regarding the air exchanges, passive 6 to 8 for a good ventilated building with mechanical ventilation for restaurants and all. 5 to 8. This is the number that is desirable for where like you need something, but that can be achieved using mechanical ways. But using purely passive, this is again like uh, like Deepa already said, that's too good to be true again, these numbers. And the last thing, it's nice to, like I said, to be promoting all the technologies, but especially AI camp for surveillance at the level of construction workers is against, in a lot of places, it is not advisable because it also transcends the privacy boundaries too. You can actually use it for performance, security, and other factors. But surveillance, like with AI, for monitoring the workers is actually, I mean, you don't have to take this quite seriously, but there are boundaries to technology and surveillance too. Just keep that in mind. Okay. Yeah, I think, like I said, overall, it's really nice to see the like all the effort that you guys put in terms of trying to bring in a lot of systems and technologies and all. But I think somewhere these the numbers and the things that you have gone actually have like I think you have to keep them very realistic. Okay, thanks. Yeah, please, you're answering this.
So you talked about the ground coverage. It is too more for the construction worker housing. So at start, I mentioned about two buildings or two construction projects. In that, one was for building and other was for road. So in building, we have very less area available. But in road infrastructure, as it is located in the outskirts, we don't have that like high cost for the land. So we tried to increase the number of units in the horizontal scattered way as we were having the available area, so we do not promote the vertical housing. So we try to like use it in a scattered way, so it was related to that.
and the main goal is mobility. So it should be like everything dismantles and packs in a unit, and you can just, it's like a can pack canister. You can just carry around anywhere, open it, and you can assemble it.
No, I was only talking about making it compact, not going high rise. Just saying things, putting things together. The more you spread, the more cost also for the site development as well. And what about the cost, like 6,000 rupees per square meter? Is it something that is checked thoroughly, like this one? The cost of the project? Rupees per square meter. Yeah.
You're talking about the baseline or the proposed one?
The that's a proposed only, right? This is the number that's on the screen. Baseline is 2,700. So, I mean, we can say that one can argue that that is using purely the sheeting material and like typically how it is built. So I'm not commenting on the, that's built up area. That's not baseline. So this is the, what is this? 6,000 rupees per square meter. Is this, that's
So
the cost, right?
it is the cost, it's a build-up cost. But here all our materials are sourced from the industry partners itself. So the costing we did was with respect to what they are providing, the rates which were provided. Even the panel right there, these are also actually made and designed by us. And the GeoGrip is modified by us. This is just a demo. It will be stronger, of course. But so everything is so, this, the whole thing is built by us, handmade. So all of this was so in-house that the cost, even the plate there, the cost is reduced to this number.
No, let me correct you. See, I love the enthusiasm. I like the amount of effort that you put in all the systems, but that number, yeah, there's not even then. Otherwise, that's even no matter whatever, whether you do it, someone else does it, like doesn't matter. That is, if that is possible, that is going to be revolutionary, right? It's going to be, that number is going to be like, it's too good. I mean, it's practically 1,000 itself, like 10,000 itself is very hard to achieve in a realistic. And with all the amazing systems that you're creating, and still managing at this is like something that is, yeah, it's like if you really achieve this, like probably millions of square foot of this thing will be at your doorstep, asking you guys to do it if you can achieve this. So, like I said, holistically speaking, you guys have done tremendous work, like the all the systems and all, like whatever you tried incorporating, a lot of research, a lot of like engineering stuff that you actually have explored and put in. But you have to be very vigilant about the numbers. Like whatever you're using, you cannot just like simple things like air exchangers and materials, like these things matter. So you have to be like very thoughtful about like how, whether you're able to achieve mechanically or whether it is passive. We haven't even gone into the other aspects like the building materials and all of that carbon footprint. You're not getting into that, but this itself is like something that you have to keep checking. Okay.
How much is the steel you have used? How much? What tonnage of steel? Steel.
600 kilograms.
600 kilograms
Kilograms.
for the full project.
Full project.
What is the area?
That's not there.
What is the area? What you have built?
Built up area is 2,765 meters square.
Meter square. Okay.
Yeah, meter square.
Square foot. Okay. 600 kgs. Right? 600 kgs. Are you sure? 600 kgs by 20,000 square foot. Huh?
600 tons. Right?
No, 600. You start from kgs to tons suddenly. So I think what I'm saying is I'm not here to, you know, just what I'm saying is there a way that so much of ton of steel out of so much of area, is it 4 kg per square foot, 8 kg per square foot? What is the norm? You know, since you are working with the builder, you basically know, no, how much is kg per square foot should be the case. So what is kg per square foot? Yeah, 2.1 is too less. Yeah.
I think we haven't worked it out specifically.
Yeah, but I think you know I think what all these things is all about curiosity. Huh? what is the market and how did we get it? Okay, you can't get like 2 kg per square foot is too less. It should be around 4 kgs. Yeah, 4 kgs, 4.5 kgs should be okay. Huh? Think about the retaining walls, and then erosion, drainage of water, everything has to be looked at. Okay, yeah, thanks.
Thank you, jury members. Thank you, Team Shramodaya.
Lot of energy.
Pardon?
You have got a lot of energy.
Thank you. Thank you.
If you allow, you will presume that. Ah. Good. Right now.
So, folks, that was our last presentation in the construction worker housing division. Okay. Our esteemed jury has shown immense dedication for assessing these entries, and I want to thank them all. So, thank you all for the thoughtful assessment and comments. And I also want to congratulate to all the finalists. As the jury coordinator for this division, I have had the opportunity to see teams submit their deliverables. They have done some incredible work. And let us not forget that these teams have discovered a new way to collaborate and do integrated design during the last 7 months. So I think that itself deserves a huge round of applause. So once again, thank you so much to our jury members for your time, feedback, and guidance. And thank you to all the finalist students for your participation. Um, in a while, we will break for tea. Now, these jury members will meet this evening and decide the winner for this division and as well as the runner-up teams. So, who will it be? Also, we have an exhibition called the Climate Smart Innovation, where you get to see innovative building products from the industry that address climate change. The exhibition is now open for you. Please proceed to the multiplex zone, which is about 5 minutes from here. And people who are online, we are going to end this stream now, but stay tuned to our channel. At 6 p.m., watch the 10 exhibitors pitch their products in a bid to win the Climate Smart Innovation Award. Until then, please have a great evening. Thank you all.
The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. The world is so hot.